Very good morning to all of you. So in today's session, we are going to learn the chemistry of aldehydes and ketones. This is the outline for the today's lecture. First, we will start with introduction. We will know what aldehyde ketones are. Then we'll go to their methods of preparation. What are the general methods that you can use to prepare aldehydes and ketones? After that, we will discuss the physical properties. We will be stressing in particular on polarity, solubility, and the volatility of the carbonyl compounds. Then we will discuss their chemical reactivity. We'll try to compare the reactivity of aldehydes and ketones, and we'll try to learn what makes aldehydes more reactive than ketones. All right. The next will be chemical reactions of aldehyde and ketones. So in today's lecture, we will be doing a very important class of reactions of aldehyde ketones. Those reactions are the nucleophilic addition reactions and the addition elimination reaction. The other reactions of aldehyde and ketones will be done in the following lecture on next Sunday. All right. And in the end, then we will summarize what we have learned today. Okay, as you can see here, aldehyde and ketones, both they have this carbonyl group, a carbon with an oxygen double bond, and attached to this carbonyl group, you have an R group, which can be an alkyl group, a aryl group, allyl, or a vinyl, and the other group attached to it, if it is hydrogen, then that particular carbonyl compound is called an aldehyde, right? And if the other group attached to the carbonyl group is also R, that is, it could be again alkyl, aryl, allyl, or vinyl group, then the compound is a ketone. Now, you've already had a session on the nomenclature of aldehydes and ketones, and you know that aldehydes, they are named as alkanals, and ketones, they are named as alkanones. These are some of the examples of aldehydes and ketones that I've put here. Now, all of you, have you used kapoor? Use kiya hai kabhi kisi ne ghar mein? That is camphor, which is a carbonyl compound. You all know that? Besides that, you have a topic called carbohydrates in your class 12 syllabus. What are those carbohydrates? Those carbohydrates are also polyhydroxyaldehydes and ketones. You know, the table sugar that you take. That is nothing but a polyhydroxy carbonyl compound. Besides that, vanilla ice creams, all of us have. That major constituent of vanilla ice cream is this compound vanillin. All of you know about cinnamon? Huh? Kitchens mein use hota hai? All of you know about that? The cinnamon, the major constituent of cinnamon is another carbonyl compound, that is cinnamaldehyde. So what you can see here is that these aldehyde ketones, the carbonyl compounds, they are widely used in our daily life. Okay? Next slide, please. Next slide. Okay. So here, what we will do now is discuss the general methods of preparation of aldehydes and ketones. There are 7 distinct methods which are used prepare aldehydes and ketones. The first of those methods is by hydrolysis of the gem dihalides. Okay. The next method that we will discuss is from alkenes. You have done alkene chemistry, you know that alkenes can be converted into carbonyl compounds by 2 reactions. One is the ozonolysis reaction and the other one is the Wacker process, right? Next, we will do the hydration of alkynes. Alkynes, you know, on hydration can be converted into aldehydes and ketones, right? Then from alcohols, you can also prepare aldehydes and ketones by doing the oxidation reaction as well as by the dehydrogenation reaction, right? Then the next reaction would be the reaction with carboxylic acids, how the carboxylic acid salts can be converted into aldehydes and ketones, that we will learn. Okay. And then the next reaction is the reaction with acid derivatives. In particular, we will learn how acid chlorides, esters, and nitriles, they can be converted into aldehydes and ketones. Okay. And in the end, we will see certain special methods which are used exclusively to prepare aromatic aldehydes and ketones. All right. So these are the 7 methods. The first method of preparation, as I said, is next slide. Yeah, this one, the hydrolysis of the gem dihalides. You can see here, this is the gem dihalide. What is a gem dihalide? A gem dihalide is a compound where you can see here you have the 2 halogen atoms which are bound to the same carbon. If you see here, when you hydrolyze it with water, what will happen? You get a diol where the 2 hydroxyl groups are bound to the same carbon. Now these compounds are not very stable. They have a tendency to undergo a loss of a molecule of water. So a water molecule will be lost and you will get the corresponding aldehyde. You see that? So depending upon the nature of the gem dihalide that you take, if you see here, there is 1 hydrogen attached to this carbon. In this case, this particular gem dihalide on reaction with water followed by dehydration will give you an aldehyde. Similarly, if you have a gem dihalide where there are 2 alkyl groups attached to the carbon, when you do the hydrolysis, it will give you the corresponding ketone, right? So I have taken one example here. What is this compound? This compound is toluene, right? So toluene on chlorination under photochemical conditions is giving you a benzaldehyde dichloride, which on hydrolysis is giving you this compound. What is this compound? This compound is benzaldehyde, right? So you can see how from gem dihalides by hydrolysis followed by a dehydration reaction, you can convert them into aldehydes and ketones. The next method of preparation is from alkenes. Now, alkene chemistry you have already studied, no? You know that alkenes, when you react them with ozone, the ozone adds across this carbon-carbon double bond and it will lead to formation of an intermediate ozonoid. Ozone adds to the carbon-carbon double bond. It forms the ozonoid, which is then subjected to a reductive hydrolysis. Zinc here is acting as a reducing medium, right? On reductive hydrolysis, what happens is you will have a cleavage taking place across this carbon-carbon double bond. Understand? When you have the cleavage taking place across this carbon-carbon double bond, each of those carbons which are joined by double bond will now get bound by a carbonyl group. So that is how you can predict what carbonyl compound you will obtain on reaction with ozone, right? You have the carbon-carbon double bond. On reaction with ozone, you form the ozonoid. And this ozonoid, when subjected to reductive hydrolysis in zinc, will give you the corresponding carbonyl compound. Just cleave this double bond and attach oxygen to each of the 2 carbons which were joined by a carbon-carbon double bond, right? So you can see here I have given you 2 examples. If you take this compound, this is 2-butene, okay? When it adds ozone followed by reductive hydrolysis, what is this compound obtained? You have got acetaldehyde. Likewise, in this case, I have taken 2-methyl 2-butene on ozonolysis followed by reductive hydrolysis. You get 1 molecule of acetone, right? And 1 molecule of acetaldehyde being formed. Now, important thing that you have to remember in this reaction is the role of zinc. Zinc is used to reduce hydrogen peroxide which is formed as a byproduct in this reaction. If you don't use zinc, what will happen is the hydrogen peroxide which is formed as a byproduct, it is an oxidizing agent. So it will oxidize the aldehyde which is formed to corresponding carboxylic acid. That is why the role of zinc is important, so that it does not allow the oxidation of aldehyde to the corresponding carboxylic acid, right? Next reaction. The second method of preparation is the Wacker process. Now, Wacker process, I'm sure you have learned, is an industrial process which is used actually to prepare acetaldehyde in the industry. It involves the use of palladium chloride in water in presence of cupric chloride and air as a co-oxidant. That means palladium chloride ke saath mein cupric chloride or air both are acting as oxidizing agents. And the alkene I have taken here is a ethene. Okay? Ethene is being converted into acetaldehyde here. And if I start with propene, I get, what is this compound? This compound is acetone. I get acetone. Now, again, what is the role of cupric chloride and air in this reaction? Now, what happens here is when this reaction is taking place, palladium chloride is a catalyst. So palladium is present in the +2 oxidation state. During oxidation reaction, the palladium 2 is reduced to palladium 0. Okay? Now, what cupric chloride does is, cupric chloride is an oxidizing agent for this. So it will oxidize palladium 0 back to palladium 2. Because palladium catalysts are very expensive, you know, the cost of production will be very high if palladium is not recycled. So the advantage of using cupric chloride here is that palladium which is formed here will be reoxidized to palladium 2 and the cost of production goes down, right? So that is the preparation of aldehydes and ketones that you can do by the Wacker process. Okay, the next reaction. The next reaction is the hydration of alkynes. Now, alkyne chemistry also you have done. You know that the addition of water molecule takes place across the carbon-carbon triple bond, and the addition follows the Markovnikov rule. The Markovnikov rule says that the positive part of the addendum adds to the carbon having more number of hydrogens attached to it, right? So when you have, this is a propyne, right? Propyne will add a molecule of water and it will form an enol. Double bond with a hydroxy compound, it is an enol. These enols are not very stable. These enol will quickly tautomerize and you will get the corresponding carbonyl compound. Okay? Now please understand here, because you are starting with alkyne, hydration of alkynes cannot give you formaldehyde. It is a one carbon compound, so that you cannot prepare by doing the hydration of alkynes. The other important thing is that the addition of water molecule is taking place across the carbon-carbon triple bond in accordance with the Markovnikov's rule, right? The next method. The next method is the method of preparation of carbonyl compounds from alcohols. Now, alcohols can be converted into carbonyl compounds by doing two different processes. The first is by using oxidizing agents. You can use strong oxidizing agents like acidified or alkaline potassium permanganate. You can use acidified potassium dichromate. You can use chromic acid, or you can use other reducing agents, which we'll be talking about. These are PCC, PDC, or the Collins reagent. Okay, so that is one method. By oxidation of alcohols, you can prepare the aldehydes and ketones. The other method of preparation of aldehydes and ketones from alcohols is by the dehydrogenation reaction. Okay, so let us first concentrate on these oxidation reactions. Now, depending upon the nature of alcohol that you take, you will get the corresponding carbonyl compound. For example, if I start with a primary alcohol, I have taken ethanol here is a primary alcohol, right? When I do oxidation with these strong oxidizing agents like potassium permanganate or potassium dichromate or even chromic acid, the first product that is formed will be the corresponding aldehyde. However, these oxidizing agents, being very strong oxidizing agent, the oxidation reaction cannot be arrested here. It cannot be stopped here. So if the aldehyde is allowed to remain in the reaction mixture, it will get oxidized to the corresponding carboxylic acid. Okay? So what we can do, if I want to use oxidation method by using any of these oxidizing agents to prepare aldehyde, the simplest thing that I can do is that I allow the reaction to take place at a temperature which is slightly higher than the boiling point of the aldehyde. Please remember that the boiling point of aldehydes are lower than those of the corresponding alcohols, right? For example, this compound is benzyl alcohol. This is the primary alcohol. When I do oxidation with acidified potassium dichromate, the initial product formed will be the corresponding aldehyde, that is benzaldehyde, right? And if I allow benzaldehyde to stand in the reaction mixture, it will get converted into, very good, benzoic acid. Now what I can do here is, the boiling point of benzaldehyde is about 178 to 179 degrees centigrade. Okay? Whereas the boiling point of benzyl alcohol is about 205 degrees centigrade. So if I allow my reaction to take place at about 180 to 185 degrees centigrade, what will happen is that whatever benzaldehyde is being formed in the reaction mixture, it will keep on getting distilled. So benzaldehyde will not remain in the reaction mixture to get oxidized, right? So if I have to use this oxidation method as preparation of aldehyde, I should allow the reaction to take place at boiling point slightly higher than the boiling point of aldehyde, so that the aldehyde gets distilled over and it is not remaining in the reaction mixture for the oxidation reaction to take place, right? Similarly, the other alternative that I can do is I use a milder oxidizing agent. I don't want the aldehyde to get oxidized to carboxylic acid, then I use a mild oxidizing agent. Mild oxidizing agents that I can use are, you can see so you can, any one of these oxidizing agents, they are PCC. PCC is pyridinium chlorochromate, or you can use pyridinium dichromate, or you can use Collins reagent, that is chromium trioxide and pyridine, right? Now, the advantage of using these oxidizing agents is because they are mild oxidizing agent, the oxidation you can see here, the reaction is arrested at the aldehydic state and it will not go on to give you the carboxylic acid. Okay? So there's one example. Here again I have taken of a primary alcohol and PCC is being used as the oxidizing agent. And another important thing that you should note here is, because they are mild oxidizing agents, they are not attacking the double bond. So double bond is retained in the reaction, right? Next slide. Now here I have given you some examples of secondary alcohols. Secondary alcohols on oxidation will give you the corresponding ketone, right? Primary alcohols on oxidation give you aldehydes. Secondary alcohols on oxidation will give you ketones, right? So one example I have taken here, this is cyclohexanol, right? On oxidation with PCC, the corresponding ketone will be obtained, and this compound is cyclohexanone. Right? Next slide. The next oxidation method is the open-hour oxidation. Open-hour oxidation is exclusively used for oxidation of secondary alcohols, right? Now, the reaction involves oxidizing secondary alcohols with this reagent, which is aluminium tertiary butoxide, okay, to the corresponding carbonyl compound, and this oxidation takes place in presence of acetone, only for secondary alcohols. The advantage of using aluminium tertiary butoxide is that the tertiary butyl alcohol will be formed as a byproduct in this reaction. Is not oxidized under the reaction conditions. So it is not interfering in the reaction. Is that okay? So you can convert your secondary alcohols into the corresponding ketones, and this tertiary alcohol which is obtained as a byproduct will not interfere in the reaction. All right. Next slide. The next method to convert alcohols to aldehydes and ketones is by dehydrogenation with copper. You know, the dehydrogenation with copper can be done at 300 degrees centigrade. If you have a primary alcohol, for example, I have taken ethanol here. On dehydrogenation with copper, it will give the corresponding aldehyde, that is acetaldehyde. Likewise, if you have a secondary alcohol, I have taken isopropyl alcohol here. On dehydrogenation with copper, it will give the corresponding ketone, that is acetone, right? The next slide. The next method of preparation is from carboxylic acids. Now, the calcium salts of carboxylic acids, when they are subjected to dry distillation, they can give you aldehydes and ketones. Depending upon the choice of the calcium salt of carboxylic acid that you take, you can get the corresponding aldehyde or ketone. For example, if I'm using 2 molecules of calcium formate, I have shown how the cleavage is taking place. You will get 1 molecule of formaldehyde, HCO from there and hydrogen from here. So you get HCHO, that is formaldehyde being formed here. If I use a mixture of a higher homologue of formic acid, what is this compound here? This is calcium acetate, right? And calcium acetate, if I combine with calcium formate, you can see how the cleavage has taken place. CH3 coming from here and CHO coming from here. So you get 1 molecule each of acetaldehyde being formed here. So if you are using calcium formate as one of the molecules, in that case, you will get aldehyde as the product. However, if you use 2 molecules of the higher homologue, जैसे आपने calcium acetate use किया, or you use higher homologues of calcium formate, in those cases, the product obtained will be a ketone. So if you are using calcium formate, you will get aldehyde. If you are using higher homologues of calcium formate, the product obtained will be a ketone. Now you understand one thing here. If I take a mixture of calcium acetate and calcium formate, now only calcium acetate will not react with calcium formate. Besides this, you will also have calcium acetate reacting with itself, right? And also you will have calcium formate reacting with itself. So this method, you know, of dry distillation of calcium salts of carboxylic acids is not a very good method to prepare aldehydes and ketones, because here you will get a mixture of products. For example, in this case, besides the formation of acetaldehyde, I will also have formaldehyde being formed. I will also have acetone being formed here, right? But if I want to prepare cyclic ketones which are having 5 or 6 membered ring. This method is very, very useful. I will give you one example. This is a calcium salt of a dicarboxylic acid, that is adipic acid. Know what is adipic acid? Now, when this is subjected to dry distillation, what will happen? You will have a molecule of calcium carbonate going, and this carbon will get attached to this carbon, and you will get the corresponding cyclic ketone being formed. So this will be a 1, 2, 3, 4, 5, a 5-membered ring being formed. So you will get cyclopentanone being formed here, right? Next slide. The next methods of preparation is from the acid derivatives. So I told you that we are going to use 3 different acid derivatives and convert them into aldehydes and ketones. The first of those acid derivatives is the acid chloride. Okay, the acid chloride can be converted into both aldehydes and ketones. Now, to convert acid chlorides to aldehyde, there are 2 different methods which are available. One is a name reaction that is called the Rosenmund reduction. So if you take acid chloride and you reduce it with hydrogen in palladium, which is precipitated on barium sulfate, and you add little bit of sulfur or quinoline as poison, the reduction of acid chloride will give you the corresponding aldehyde being formed, right? For example, I have taken here, this is acetyl chloride. When you subject it to this 2-carbon acid chloride, when you do the reduction, it will be converted into the 2-carbon aldehyde, that is acetaldehyde here, right? The other way to convert acid chlorides into aldehydes is by using this reagent. This is called lithium tri-tertiary butoxide aluminium hydride. Okay. That is the reducing agent we have used, lithium tri-tertiary butoxide aluminium hydride. Now you have heard of lithium aluminium hydride. Okay? Lithium aluminium hydride, if you use here, the acid chloride will be reduced to primary alcohol. That is why we cannot use lithium aluminium hydride. We have used here lithium tri-tertiary butoxide aluminium hydride, which is a weaker reducing agent than lithium aluminium hydride. So it will reduce the acid chloride to the corresponding aldehyde, right? Again, I have taken this example here. You can see you have a 2-carbon acid chloride. which is being converted into the 2-carbon aldehyde, that is acetaldehyde, right? Next. Now, if you have to convert the acid chlorides into ketones, we react them with what we call the Gilman's reagent. Gilman's reagent is nothing but dialkyl cadmium. How do you prepare dialkyl cadmium? Dialkyl cadmium can be prepared by reaction of Grignard reagent with cadmium chloride. So you'll get the corresponding dialkyl cadmium. Now, acid chloride, when you react with dialkyl cadmium, what will happen is this Cl here in the acid chloride will be replaced by this R group here. Okay? So for example, R group here is ethyl group here. I have taken diethyl cadmium. So this Cl here will be replaced by ethyl group. So I get this corresponding ketone being formed. You understand what is happening in the reaction? Simply replace this Cl by this R group here and you get the corresponding ketone. For example, acetyl chloride, when I react with diethyl cadmium, it is getting converted into this carbonyl compound. What is this compound? This compound is ethyl methyl ketone, right? So acid chlorides, you can convert them into ketones by reaction with Gilman's reagent, and acid chlorides can be converted into aldehydes by either using Rosenmund reduction or you can use lithium tritertiary butoxide aluminium hydride. Next slide. The next set of methods is the preparation of the aldehydes and ketones from nitriles. Okay, now nitriles can be converted into ketones on reaction with Grignard reagent. If you can see Grignard reagent here, it will react with nitrile. R group is nucleophilic because of the electropositivity of the magnesium. It will attack carbon here. You get this compound, which on hydrolysis will give you the corresponding ketone, right? That is how the reaction is taking place. You can see here, I have shown here how the Grignard reagent attacks the nitrile and you get the corresponding ketone being formed, right? In case you want to prepare aldehyde from Grignard reagent, instead of using alkyl nitrile, we can use the HCN gas, okay? HCN on similar reaction, see what has happened here is, this R here now has been replaced by H, okay? So you will get the corresponding aldehyde being formed here on the same reaction. So alkyl nitrile, if you react with Grignard reagent, you will get a ketone. And if you react HCN with Grignard reagent, you will get aldehyde. Besides this, nitriles can also be converted into aldehydes by doing two different reactions where we are doing a selective reduction. See, if you have nitrile, if you do a complete reduction, they will be reduced to amines. So what we are doing here is, we are doing a selective reduction followed by hydrolysis. So kya kiya hai? The first method is, this reaction is called Stephen's reaction, where the alkyl nitrile is reduced with tin chloride and HCl. The product obtained is an aldimine. And this aldimine can be hydrolyzed to corresponding aldehyde. Yahan pe. Okay? It is converted into corresponding aldehyde. Likewise, there is another reducing agent that is called dibal H, diisobutyl aluminium hydride, right? You can reduce the alkyl nitrile with dibal H, convert it into aldimine, again hydrolyze it to the corresponding aldehyde. Okay? So nitriles can be converted into ketones on reaction with Grignard reagent, and nitriles can be converted into aldehydes by doing a Stephens reaction or by reduction with dibalate followed by hydrolysis. The next method of preparation is from the esters. Now, you have done the alcohol chemistry, and you know if you start with if you start with the esters, for example, you start with ethyl formate and you are reacting it with Grignard reagent, you will first get what? You first get a aldehyde, but this will further react with Grignard reagent and you will get the corresponding primary alcohol. Likewise, if you start with the higher esters of formic acid, higher homologues of formic acid, you will get the corresponding ketone being formed, which on further reaction with Grignard reagent forms a tertiary alcohol. You have done these reactions to prepare alcohols. Now, that means you cannot react Grignard reagent with ethyl formate or higher homologues of formic acid ester to prepare aldehydes or ketones. However, we can use something called a orthoformic ester. The compound that I have taken here is ethyl orthoformate. Okay? This orthoformic ester, you can react with Grignard reagent. So what happens here is that you will have a acetal being formed here. Now, acetals are not reactive under these reaction conditions, so the reaction will not proceed further. Okay, the advantage with acetals is that they can be hydrolyzed to the corresponding carbonyl compound. So once you have this acetal being formed, it will be hydrolyzed to the corresponding aldehyde. Okay, so if I start with the ortho ester of formic acid, see here you have hydrogen. When you have hydrogen here, this is an ortho ester of formic acid. You can prepare the corresponding aldehyde, and if you replace this hydrogen by R here, and do the Grignard reagent reaction, you can prepare the corresponding ketone. Follow me? So instead of using esters, you can use ortho esters to convert Grignard reagent to aldehydes and ketones. Is that all right? The next reaction. Now, having discussed all the general methods for preparation of aliphatic aldehydes and ketones, now we will come to certain specific methods which are used to prepare only aromatic aldehydes and ketones. Okay, this first method is this reaction from toluene. We are doing oxidation of toluene. The oxidizing agent used can either be chromium trioxide in presence of acetic anhydride, and the product obtained is benzaldehyde. The advantage of using chromium trioxide here is that the moment benzaldehyde is formed, okay, it will react with benzaldehyde to form benzylidene diacetate. Now, because of formation of this benzylidene diacetate, benzaldehyde will not be oxidized to benzoic acid. So it is preventing the further, otherwise if you allow benzaldehyde to remain in the reaction mixture, it will get oxidized to benzoic acid. So the advantage of using acetic anhydride is that the moment benzaldehyde is formed, it converts them into benzylidene diacetate. So it is preventing the further oxidation. And this benzylidene diacetate can be hydrolyzed to generate benzaldehyde. Okay, Similarly, if you see in this reaction, we have used chromyl chloride. Again, the formation of this brown colored complex. Like in case we have got a benzalidene diacetate here. Similarly, you have a chromyl chloride complex being formed here, which prevents further oxidation of benzaldehyde to benzoic acid. So this brown complex, when you hydrolyze, you will get benzaldehyde. Right? This reaction where you are using chromyl chloride as the oxidizing agent is called the Aldehydes reaction. Okay? So these two reactions you have seen how alkyl benzenes can be converted into the corresponding aldehyde. Right? So we have taken toluene and we have converted it to benzaldehyde. Next reaction. The next two are the name reactions which we have used here. The first reaction is nothing but a formylation reaction, and that reaction is called the Gutterman-Koch reaction. You take an aromatic hydrocarbon, react it with carbon monoxide, HCl, in presence of a Lewis acid like AlCl3, and you will have a formylation reaction taking place. CHO gets attached to the benzene ring. So you get, if you start with benzene, you will get benzaldehyde being formed, right? The other reaction is a formylation of phenols. This reaction is used to prepare phenolic aldehydes, right? If you have phenol reacted with chloroform in aqueous NaOH at 60 to 70 degree, it will lead to formation of a mixture of products, that is orthohydroxybenzaldehyde and para-hydroxybenzaldehyde. However, orthohydroxybenzaldehyde, that is commonly called salicyl aldehyde, will be the major product. Okay, the reaction preferably takes place at ortho position. If, however, you have a phenol where the ortho position is occupied, for example, if I start with this phenol, and if I do the Riemer-Teimer reaction here, because the ortho position is occupied in this case, my formyl group will go to the para position. In that case, you will get a para substituted product being formed. Okay? So this is Riemer-Teimer reaction, which is used to prepare the phenolic aldehydes. Next reaction. The last of these reactions is the Fiedel-Crafts acylation reaction, which is used exclusively to prepare aromatic ketones. The reaction involves reacting aromatic hydrocarbon with acid chloride in presence of Lewis acid catalyst like aluminum chloride. So you have the acyl group, RCO group, which gets attached to the benzene ring. So I have taken two examples here. If I start with acetyl chloride, so you will have a CS3CO group, that is the acetyl group, which gets attached to the benzene ring. And if I start with this compound, this is called benzoyl chloride. Okay, so you will have a benzoyl group being attached to the benzene ring, and the compound formed will be called a benzophenone. Both these reactions are examples of electrophilic substitution reactions on the benzene ring, which you might have done in the aromatic hydrocarbon chemistry, right? So we have discussed all the general methods to prepare aldehydes and ketones. Let us quickly summarize what all methods we have done before we go on to the questions. Okay, so this is the first method that we did. We said that if you have gem dihalides, you can do the hydrolysis followed by dehydration. You can convert them into the corresponding carbonyl compound, right? And if you have alkene, you can do either ozonolysis or you can do the Wacker process and you can convert them into the carbonyl compound, right? If you have alkynes, you can do hydration in accordance with Markovnikov rule and you can convert them into aldehydes and ketones. And if you start with alcohols, you can do either the oxidation reaction or you can do dehydrogenation reaction and you can convert them into carbonyl compound. Calcium salts of carboxylic acid, when you dry distill, they can be converted into aldehydes and ketones. And we have learned that this method will be useful only if you use calcium salts of dicarboxylic acid, and it can be used to prepare cyclic 5 or 6 membered ketones, right? Next, the acid derivatives and nitriles, they can be converted into carbonyl compounds either by doing a selective reduction or by reaction with organometallic compounds like Grignard reagent or the Gilman's reagent, right? And finally, we have learned certain special methods to prepare aromatic aldehydes and ketones. Next, we'll go on to the questions. Okay, before we do that, let us discuss the general physical properties of the carbonyl compounds, the boiling points. If you see, I have written the trend for the boiling point of the carbonyl compounds. You can see here. The boiling point follows the orders alkanes or ethers less than aldehyde ketones, which are less than alcohols, which will be less than the corresponding carboxylic acids. Now you can see that aldehydes and ketones, if I write the structure, I've shown in the next slide. The next slide, please. Yeah. You can see, because there is electronegativity difference between carbon and oxygen, the pi electron cloud gets polarized, because of which the carbon gets a positive charge and oxygen gets a negative charge. So the carbonyl compounds, they are acting as polar molecules, and because of their polarity, they will have weak dipole-dipole type of interactions. Okay? Because of which they will have higher boiling points than the corresponding hydrocarbons. Right? However, their boiling points will be lower than those of alcohols or carboxylic acids, because unlike alcohols and carboxylic acids, aldehydes and ketones cannot form hydrogen bonds. Alcohols and carboxylic acids, they form hydrogen bonds. That is why they have higher boiling points and melting points than corresponding carbonyl compounds. Okay, let's go back. Next slide. इससे पहले वाला slide. पीछे वाला. Yeah. The next is the solubility in water. Now, being faintly polar compounds, like ethers, carbonyl compounds can only act as hydrogen bond acceptors. So they form weak hydrogen bonds with water molecules. They cannot act as hydrogen donors, right? The compound to form hydrogen bonds, it can either act as a hydrogen acceptor or it can act as a hydrogen donor or both. Now, carbonyl compounds like ethers are only hydrogen acceptors. So they form weak hydrogen bonds. Next slide. Now, see here, I have shown they form weak hydrogen bonds with water molecule. So you will find that the lower members of the family, they will be highly soluble in water. But as the length of the carbon chain goes on increasing, you will find that their solubility will decrease. I will just give you one example here. What this compound is acetone. And the other compound is ethyl methyl ketone. Now this being a 3-carbon ketone and this being a 4-carbon ketone. If you see the solubility, acetone is highly soluble in water. Whereas when you go to ethyl methyl ketone, it is only partly soluble in water. So you find that as the chain length increases beyond C5, 5-carbon chain, you will find that the solubility will drastically drop. So the lower members of carbonyl compounds only are soluble in water. Is that okay? Next. Okay. Now let us take up some questions which based on all that we have discussed so far before we go on to the reaction. This first question we have done. So what will be the product form? What is this compound? This is calcium adipate. Can you recognize this compound? Huh? So on dry distillation, you will get cyclopentane. Okay. Next, let us go on to the next reaction. Ozonolysis of an organic compound A produces acetone and propionaldehyde in equimolar mixture. identify A. So let us write what are those two compounds that you are getting. One compound is acetone and the second one is now. In order to identify the carbonyl compound, all you have to do is remove these oxygens and join the carbons which were joined to oxygen with one another, right? So the alkene that you should have is so what will be this compound? This compound will be 2-methyl pentastuene, right? Okay. The next question is, you have this alkyne given. It is subjected to hydration reaction. You have to predict the product which is formed. Can you see? We have learned that the addition of molecule of water in case of alkyne takes place in accordance with the Markovnikov rule, right? So what will happen? This is your compound, right? Now when the proton adds, proton can either add to this carbon or it can add to this carbon, right? So what will happen is, you can either get can you see? When hydrogen adds here, you will get this carbocation being formed. And when the hydrogen adds here, you will have this carbocation being formed. Now, where the hydrogen adds will depend upon the stability of the carbocation being formed. You can see here, this is a benzyl type carbocation where the plus charge can get delocalized onto the benzene ring. If I just write it like this, right? The plus charge can get delocalized onto the benzene ring. So this carbocation should be more stable than this carbocation, right? So the proton will add in this direction. So when the proton adds in this direction, then water molecule will attack here. Okay? So when the water molecule attacks here, then there will be a deprotonation taking place. And what is this? I told you this is an enol being formed, and these enols are not stable. So the moment the enol is formed, it will tautomerize. It will tautomerize. And the compound obtained will be the corresponding ketone. Clear? So any problem there you have seen? How the carbocation has been formed, and after the formation of carbocation, water molecule will attack. After attack of the water molecule, you will have a loss of a proton taking place, and this loss of proton will generate an enol. The enol not being stable, it will quickly tautomerize to form the corresponding ketone, right? The next question is, which of the following will give propionaldehyde on dry distillation? So if you remember, I told you if you start with calcium formate, your CHO will come from there. Okay? So CHO will come from calcium formate, and you see where the remaining group will come from. Which of these three will give you now propionaldehyde? See, you have two options here. Only two of them have calcium formate. The third one does not have calcium formate, because this, when you subject it to dry distillation, will give you a ketone, right? Because you have used two molecules of calcium acetate. So this is ruled out. Now between this and this, you can see here, this is a phenyl ring here. Okay? So that cannot give you a propionaldehyde. You have a 2-carbon chain coming from here, CH3, CH2 coming from here, and then you will have a CHO coming from the calcium formate. So the correct option will be B. So by using these two, you can prepare the propionaldehyde. Correct? The next question. I've given you a set of 4 compounds, and you have to arrange these 4 compounds in the increasing order of their boiling point, that is starting from the lowest to the highest. You can see what are, please identify what are the functional groups which are present here. What is the functional group here? Aldehyde. What is the functional group here? Alcohol. And here you have, what is the functional group? Ether. This is an ether, right? And this is a alkane. So now please arrange them in the increasing order of their boiling point. So what will be the? Exactly. So the correct answer will be correct? Okay. Right. The next question is, carbonyl compounds have higher dipole moment than alcohols. Explain. Now what it means is you have to explain what makes carbonyl compounds more polar than alcohols. Please understand, alcohols also have a carbon-oxygen bond, and the carbonyl compounds also have a carbon-oxygen bond. The difference here is the presence of pi electrons, which are present in case of the carbonyl compounds. The pi electrons are weakly held. Hence, they can be easily polarized as compared to sigma electrons, which are present in the case of alcohol. Right? So that is why you find, because of the easy polarizability of the pi electrons present in the carbonyl compound, the carbonyl compounds, they will have higher dipole moment than the corresponding alcohol. Okay. In the next question, you have to identify what is X. You can see what is this reaction. This is the reaction for conversion of alkyl nitrile to the corresponding dibar H, or one more reaction we can do. Stephen's reaction. We can use tin chloride HCl. So either of these two reactions you can use, either dibar H, or you can do the Stephen's reaction to convert the nitrile into the corresponding aldehyde, right? The next question is, dialkyl cadmium is preferred over Grignard reagent for preparation of ketones from acid chlorides. See, we have learned that if you have to convert acid chloride to ketones, we prefer using Gilman's reagent, that is dialkyl cadmium, which is an organometallic compound, but we do not prefer using Grignard reagent, which is another organometallic compound. What could be the reason? Between Grignard reagent and Gilman's reagent, which is more reactive? Because magnesium is more electropositive, the Grignard reagent is more reactive. So if Grignard reagent is more reactive, what will happen if I react acid chloride with Grignard reagent? The first product formed will be a ketone. But because of the higher reactivity of Grignard reagent, the reaction will not stop there. It will proceed further and the compound obtained will be a no. Okay, you will get a ketone being formed, but if you react, this will react further, and this reaction you have done in preparation of alcohols. Ketones react with Grignard reagent to form tertiary alcohol. So the reaction will not stop at the ketonic stage. It will react further and the product obtained will be a tertiary alcohol. That is why Grignard reagent is not preferred to convert acid chlorides to ketones. Right? Okay. Next, we have three conversion reactions. The first is the conversion of 2-butene to ethanol. Let us see how we will do this. Please write down the reaction and see how you can convert but2ene to ethanol. So what is that reaction that we have learned for conversion of alkenes to carbonyl compounds? What is that reaction? Ozonolysis reaction. So what we will do is, we will do ozonolysis followed by reductive hydrolysis. When what will happen? You have a cleavage taking place across the carbon-carbon double bond, and the carbon which are linked by a double bond will now get attached to oxygen. So the product formed will be two molecules of ethanol or acetaldehyde, right? Will be the product. Correct or not? Okay. Now let us attempt the second reaction. You have to convert para-nitrotoluene to para-nitrobenzaldehyde. What reagent will you use? To convert para-nitrotoluene to para-nitrobenzaldehyde. We have learned one reaction by which, what is this reaction? Nothing but conversion of alkyl benzene to the corresponding aldehydes, right? So what is that reagent that you use here? The reagent used here is, you can use chromyl chloride or you can use chromium trioxide in acetic anhydride, right? Right? When you do the reaction with chromium trioxide in acetic anhydride, the product is a benzalidene diacetate, and that benzalidene diacetate on hydrolysis will form the corresponding aldehyde, right? So by this reaction, you can convert para-nitrotoluene to para-nitrobenzaldehyde, right? The next reaction, let us see. Please write the reactant and write the product. This is the reaction. You have to convert 1 but1-ine to 2-butanone. Okay, what reagent we have? One reaction we have learned. For alkynes, by which you can convert them into carbonyl compound. What is that reaction? How can you convert alkynes into carbonyl compounds? By hydration of alkynes. Okay, very good. Let us do the hydration of alkynes. So you reacted with water in presence of sulfuric acid and mercuric sulfate as catalyst. The addition of water will take place in accordance with the Markovnikov rule. So hydrogen will add on to this carbon and the OH will add on to this carbon, right? And the product obtained will be again you will have the enol being formed, and the enols not being stable will quickly tautomerize. To the corresponding ketone. Clear with everybody? So with this we have finished first half of the lectures. We have discussed the different methods of preparation of aldehyde ketones and we have taken up questions on their boiling point and the other physical properties, right? Next we will go on to the reactions of carbonyl compounds. Now carbonyl compounds, that is the aldehydes and ketones, they are highly reactive compounds. The reactivity of carbonyl compounds is again because of the electronegativity difference between the carbon and the oxygen, because of which the carbon is acquiring a partial positive charge and the acts as a electrophilic center, and the oxygen is acting as a nucleophilic center because it is acquiring a partial negative charge. So the most of the reactions of carbonyl compounds are because of this electronegativity difference, the carbon being the electrophilic center and oxygen being the nucleophilic center. The other category of reactions which we'll be studying in the next class would be the one where because of the inductive effect of the carbonyl group, the hydrogen occupying the adjacent carbon will be acidic. So those will be the reactions which will be characteristic of the acidic character of the hydrogen occupying the alpha carbon. Okay. Then we will learn what makes aldehydes more reactive than ketones. Okay. The next slide, please. So what I have done is I have divided the reactions of aldehydes and ketones into 5 different categories. The first set of reactions which we are going to discuss today is this reaction, an important reaction of carbonyl compounds, that is the nucleophilic addition reactions. Along with nucleophilic addition reactions, here we will also study nucleophilic addition elimination reactions. Okay, so the first category of reactions. The next category of reactions is the reduction of carbonyl compounds. Depending upon the nature of reducing agent that you use, aldehydes and ketones can be converted into either alcohols or alkanes. Okay, the reduction reactions of carbonyl compounds. Next, we will see the oxidation reactions of carbonyl compounds, where they will be oxidized to carboxylic acids having same number of carbons in case of aldehydes, and carboxylic acids having fewer number of carbons in case of ketones. Okay. The next set of reactions will be the reactions with alkali. Just now I told you that the alpha hydrogen, the hydrogen attached to the alpha carbon is highly acidic. These will be the reactions which are due to the acidic character of the hydrogen on the alpha carbon, the reaction with alkali. And finally, some other reactions which I have grouped them under miscellaneous reactions. Okay. So what we are going to do today is we are going to concentrate on this. We will study the nucleophilic addition and nucleophilic addition elimination reactions of the carbonyl compounds. Next slide. Now, the nucleophilic addition reaction of carbonyl compounds can take place in 2 different ways. First is the reaction with strong nucleophiles like the cyanide ion or the bisulfite ion or with the Grignard reagent. These will be simple addition reactions where what will happen is you will have addition reaction taking place across the carbon-oxygen bond. Okay, this will be the first set of reactions that we are going to study. The second set of reactions will be the addition reactions followed by elimination. We will learn how by doing these reactions we can convert a carbon-oxygen double bond to a carbon-nitrogen double bond. So all these reactions will be addition reactions followed by elimination, and all these reactions are catalyzed by mild acid. Okay, so these 2 categories of nucleophilic addition reaction that we are going to concentrate on today. Next slide. Yeah, just now I said that the nucleophilic addition reaction on carbonyl compounds can take place in 2 ways. First is where you have reaction with a strong nucleophile taking place. Now those reactions, they proceed in 2 steps. What will be those 2 steps? In the first step, the nucleophile will attack the electropositive carbon, okay, to generate a 4-membered alkoxide, and then that alkoxide will take up a proton from the solvent. So there are 2 steps: the nucleophilic attack on the electropositive carbon center followed by protonation. The result will be addition across the carbon-oxygen double bond. We will show in the next slide. You can see here the nucleophile. Normally negatively charged nucleophiles will undergo these type of reactions, will attack the electropositive carbon center. The pi electron cloud of carbon-oxygen bond get polarized. Okay, so you have this kind of 4-membered alkoxide ion being formed. This negatively charged oxygen will then take up a proton from the solvent. Okay, so a protonation reaction taking place in the next stage, and you will have this 4-membered addition product being formed. You can see here what has happened here is addition taking place. Nucleophile adds to carbon and the hydrogen adds to oxygen. Okay, resulting in formation of a 4-membered addition product. The important thing that you have to remember here is that when all these addition reactions take place, there is a change in hybridization of the carbon. What is the hybridization on the carbon here? It is sp2 hybridized. So when the addition takes place, the hybridization of the carbon changes from sp2 to sp3. So initially there were 3 atoms or group of atoms which were surrounding the carbon, right? The central carbon atom. On addition, when you get this addition product, there are now 4 atoms or group of atoms surrounding the carbon. So you can see that the crowding, it is the increase in crowding around the central carbon atom which is going to determine the rate of this nucleophilic addition reaction. You will find the difference in reactivities of different aldehydes and ketones is because of increased crowding around this central carbon atom when these nucleophilic addition reactions take place. You understand what I said? There were initially 3 atoms or group of atoms around carbon. When the addition reaction has taken place, the number of atoms, group of atoms surrounding carbon has now increased to 4. So there were initially 3 groups, now there are 4 groups. So there is smaller space, there is a less space available for all those 4 groups to accommodate. So they are very close to one another, you have steric crowding, which will destabilize the molecule. Now depending upon the stability of that 4-membered addition product that you are forming, the rate of the nucleophilic substitution reaction will be determined. Clear? Next slide. This is the second set of reactions I told you. The acid catalyzed nucleophilic addition reactions. Now, acid catalyzed nucleophilic addition reactions will take place with weak nucleophiles. Nucleophiles, of this type, normally they are called ammonia derivatives. Because they are weak nucleophiles, they cannot attack directly the weakly electropositive carbon center. Okay, so what happens is they require protonation in the first step. So what does protonation do? When the protonation takes place, you can see here, on the oxygen, the pi electron cloud will get delocalized towards oxygen. As a result, what happens? The carbon acquires a positive charge. So the role of protonation reaction is to increase the electropositivity of the carbonyl carbon. It is making the carbonyl carbon more electropositive so that a weak nucleophile can also attack. When there were strong nucleophiles, you did not require protonation because strong nucleophile can directly attack the weakly electropositive carbon. When you have a weak nucleophile, you are adding a proton first so that protonation is increasing the electropositivity of the carbonyl carbon and facilitating the attack of a weak nucleophile. Okay? So the first step in the reaction is protonation reaction, because of which this carbon is acquiring a positive charge and it is becoming more electropositive. In the next step, now this positively charged carbon now can be attacked by this weak nucleophile. Okay? The addition reaction will be same. Again, you have got a 4-membered addition product being formed. Addition taking place across the carbon-oxygen double bond, right? Now, this 4-membered addition product is formed. In the next stage, what will happen? There will be deprotonation reaction taking place. This nucleophile has a positive charge because it has given its lone pair of electrons to the carbon. So, this proton will be lost. So, deprotonation reaction taking place to give you this 4-membered addition product being formed. Okay? So in case of strong nucleophiles, direct attack of the nucleophile followed by protonation, the addition taking place in 2 steps to form a 4-membered addition product. In case of weak nucleophile, you first have protonation, carbon becomes positively charged, then the nucleophile will attack, and then the nucleophile finally loses a proton to form a 4-membered addition product. Right? So these are the 2 major mechanisms of nucleophilic addition reaction on the carbonyl carbon. Okay? Now before we take up individual examples of nucleophilic addition reactions, let us discuss the relative reactivity of aldehydes and ketones towards this nucleophilic addition reaction. Now, I told you that when the addition takes place, there is a change in hybridization from sp2 to sp3, and you're getting a 4-membered addition product being formed. So the formation of that 4-membered addition product largely determines the order of reactivity. What makes aldehydes more reactive than ketone, we are going to discuss here. There are 2 important factors which contribute to the higher reactivity of aldehydes as compared to ketones for a nucleophilic addition reaction. And those 2 factors are the inductive effect and the steric effect we will be discussing now. The other thing that we will discuss here is the relative reactivity of aromatic carbonyl compounds with the aliphatic carbonyl compounds, and we will try to understand what makes aliphatic aldehydes and ketones more reactive than the aromatic aldehyde and ketones towards the nucleophilic addition reaction. Okay, so let us take up the first part. As I said, aldehydes are more reactive than ketone because of inductive effect and steric effect. Let us take inductive effect first. Now, the nucleophilic addition reactions of carbonyl compounds are because of the electropositivity of this carbonyl carbon. Okay. Now let us higher the positive charge on this carbonyl carbon, higher will be the rate at which the nucleophile can attack. That means the rate of nucleophilic attack will depend upon the electropositivity of this carbonyl carbon. Now let us take 3 compounds here. I've taken formaldehyde, acetaldehyde, and acetone. So you can see here, when you replace one of these hydrogens by a methyl group offers plus I effect. So one alkyl group here, the electropositivity of this carbonyl carbon will be less than the electropositivity of this carbonyl carbon. That means the electropositivity of formaldehyde is maximum. So the rate of reaction with formaldehyde will be maximum, right? From acetaldehyde, when you go to acetone, there are 2 alkyl groups which are offering the plus I effect. So the electropositivity of this carbonyl carbon will be minimum. That is why the rate of nucleophilic addition reaction or the rate of nucleophilic attack will follow the order formaldehyde greater than acetaldehyde greater than acetone. Okay? So that is the role of inductive effect in the order of nucleophilic addition reaction. Next, let us go to the steric effect. Now, I told you when you have the addition taking place across the carbon-oxygen double bond, initially there were 3 atoms or groups of atoms which were surrounding this carbon. And now those have been replaced by 4 atoms or group of atoms here. Okay? So when the addition reaction takes place, crowding around this central carbon is increasing. As you sequentially replace these small sized hydrogen atoms by bulkier alkyl groups. For example, from formaldehyde, when I go to acetaldehyde, the corresponding product will be this. Okay? From acetaldehyde, when I go to acetone, this hydrogen will also be replaced by an alkyl group. So as the size of atoms or group of atoms which are surrounding the central carbon go on increasing, there is an increased steric crowding which decreases the stability of the addition product being formed. That is why you found that the order of reaction of the carbonyl compounds will be formaldehyde greater than the other aldehyde and then the ketones. Next, we come to the difference or the comparison of reactivity of aromatic carbonyl compounds with the aliphatic compounds. Now, if I take one example of an aromatic compound, aromatic carbonyl compound, we can take benzaldehyde. Let us compare benzaldehyde with formaldehyde. So benzene offers a plus R effect. So you can see what is happening because of resonance is that the pi electron cloud on the benzene ring is getting delocalized. Because of the donation of electron cloud, the electropositivity of the carbonyl carbon will decrease. Now, if the electropositivity of the carbonyl compound decreases, the rate of nucleophilic addition reaction will decrease. So it is the donation of pi electron cloud from the benzene which is offering a plus R effect, which is decreasing the electropositivity of the carbonyl carbon, whereby decreasing the rate of nucleophilic addition. Also, if you compare the size, you have a bulky benzene ring which is replacing the small size hydrogen atom here. Again, when you have the addition reaction taking place, the four-membered addition product will be more sterically crowded. So also there is an increased steric crowding in case of aromatic aldehydes as or ketones as compared to the aliphatic aldehydes and ketones. So again, you have resonance and the steric effect which are responsible for the decreased reactivity of aromatic carbonyl compounds as compared to the aliphatic aldehydes or ketones. Correct? Now let us go to the next slide. We will take up some nucleophilic addition reactions of carbonyl compounds. Now, as you can see in this slide, the first reaction is the addition of alcohols. The reaction takes place in presence of acid as the catalyst. So what will happen? The acid will add and it will lead to formation of a right? It will lead to formation of a carbocation so that the now alcohol can add on to this carbocation. So basically what is happening in this reaction is this C double bond O is replaced by two molecules of OR, two alkoxy groups. You get a di-alkoxy compound being formed, which is called an acetal if you start with an aldehyde, and it is called a ketal if you start with a ketone, right? Now, what is the application of this reaction? The application of this reaction is in the industry if you have to protect the carbonyl group. Okay? Then they can be protected by formation of what we call the cyclic acetal or cyclic ketal. I will give you that reaction. So what happens here is when you take the carbonyl compound, that can be an aldehyde or it can be a ketone, and react it with a glycol. Glycols are 1,2-dihydroxy compounds. So what will happen? There will be a loss of a molecule of water taking place, and you will get the corresponding cyclic para-toluene sulfonic acid. PTS is para-toluene sulfonic acid. कोई एसिड कैटलिस्ट चाहिए ना रिएक्शन में, so the acid catalyst used here is PTS, that is para-toluene sulfonic acid. So you get the cyclic acetal being formed here. ठीक है? So अगर carbonyl compounds हैं आपके and you don't want the reaction to take place at the carbonyl compound, you react them with the glycol and they will be protected as acetal. When the reaction is over, you can hydrolyze them back with acid and you will generate your carbonyl compound back. You understand? That is the advantage of using this cyclic acetal or cyclic ketal as a protecting group. Follow? The next reaction is the nucleophilic addition of HCN. The cyanide ion, being a strong nucleophile, will directly attack the carbonyl center, and it will lead to formation of compounds that are called cyanohydrins. Okay? You have cyanide attacking the carbon and the hydrogen adding to the oxygen. So you get these compounds which are called cyanohydrins. Now this reaction can either take place with HCN gas in presence of sodium hydroxide. The reaction proceeds very slowly if you don't add sodium hydroxide. The idea of adding sodium hydroxide is to generate cyanide ion, which is a strong nucleophile. When you are doing this reaction, what will happen is you will get the sodium cyanide being formed. Now sodium cyanide ion being a strong nucleophile, now it can easily attack the carbonyl center. So you get the cyanohydrin being formed, right? You can see here I have taken acetaldehyde and you do the reaction with sodium cyanide in HCl. So you get the corresponding acetaldehyde cyanohydrin being formed. Okay? Now, the advantage of preparing cyanohydrins is that the cyanide group, can be hydrolyzed, and on hydrolysis, the cyanide is converted into what? Carboxylic acid. So cyanohydrins can be used to prepare alpha hydroxy acid. You can see this is the adjacent carbon, which is the alpha carbon to the carboxylic group, and you have a hydroxyl group attached to it. So you prepare cyanohydrin and then you hydrolyze it. Prepare cyanohydrin and then hydrolyze it, and you prepare the corresponding alpha hydroxy acid. So that is one route to prepare alpha hydroxy acids. The other thing you can do is this cyanide group, if you reduce it, let's say lithium aluminum hydride, it is reduced to the corresponding primary amine. So you can reduce it to CH2NH2 and prepare beta hydroxyamines. You can see this is alpha carbon and this is the beta carbon. So you have hydroxyl group attached to the beta carbon, right? So this is a beta hydroxyamine. So cyanohydrins can be converted either into alpha hydroxy acids by hydrolysis reaction, or they can be converted into beta hydroxyamines by doing a reduction reaction. Okay, these are the two advantages of preparing the cyanohydrins. All right, the next reaction. The next is the nucleophilic addition of the sodium hydrogen sulfide or sodium bisulfide. Sodium bisulfide, the bisulfite ion again adds on to the carbonyl carbon, and it will lead to formation of the bisulfite addition product. Now please understand there is difference in the reactivity of aldehydes and ketones. So this reaction equilibrium, you have this being formed, and the hydrogen from here is transferred here to form proton transfer to give you this compound, the bisulfite addition product. Now the direction of this equilibrium lies towards the right in case of aldehydes because of their higher reactivity. But in ketones, because you have steric hindrance, the direction of the equilibrium lies majorly towards left. So this reaction can be used for aldehydes and certain methyl ketones, okay, to prepare the bisulfite addition product, and can be used as a means of purification and separation of the aldehydes from a mixture of, say, aldehyde and ketone. For example, if you take benzaldehyde and acetophenone, acetophenone does not undergo a bisulfite addition, whereas benzaldehyde does. So if you have a mixture of benzaldehyde and acetophenone, you can react them with sodium bisulfite and you can prepare the bisulfite addition product with benzaldehyde, and the acetone will remain in solution and you can separate it. The advantage of preparing this bisulfite addition product is that this bisulfite, it can be hydrolyzed back to the corresponding carbonyl compound on reaction with dilute acid or alkali. Means if you have, say for example, for acetaldehyde, I prepare this. This will be the bisulfite addition product that you will get for acetaldehyde. I can hydrolyze it back in dilute acid or dilute alkali, and I will generate back my carbonyl compound. Okay, so that is the advantage of using this bisulfite addition reaction. Next reaction. So you can see here, I have taken two examples. Benzaldehyde undergoes the bisulfite addition product to form this bisulfite addition product here, and I have taken this is not N-butanone, this is 2-butanone, there's some mistake here, it should be 2-butanone, which adds on sodium hydrogen sulfide, and the product formed will be ठीक है. The next reaction. The next is the addition of the organometallic compound. This reaction I'm sure you have done in the methods of preparation of alcohols. You know that choosing an appropriate aldehyde or ketones, when you react them with Grignard reagent, if you are starting with formaldehyde, you can prepare a primary alcohol. If you start with acetaldehyde, you can prepare a secondary alcohol. And if you start with a ketone, you can prepare a tertiary alcohol. We will see in the reaction. First, you see here, there is a nucleophilic carbon here, right? The nucleophilic carbon, like we have discussed, all the nucleophilic addition reaction will attack the positively charged carbon center here. Pi electron delocalized. You get this addition product. This addition product, when it is hydrolyzed, it will form the corresponding alcohol, right? Next slide, please. You can see here, if you take formaldehyde, just now I told you, if you start with formaldehyde, you will get a primary alcohol being formed as a product, right? If you start with the higher aldehyde, acetaldehyde or higher homologues, you start with, you will get a secondary alcohol being formed as a product. And if you start with ketones, the product obtained will be a tertiary alcohol. Okay? So you can convert them into tertiary alcohols. So formaldehyde will give you primary alcohol, higher aldehydes will give you secondary alcohols on reaction with Grignard reagent, and ketones on Grignard reagent reaction will give you a tertiary alcohol, right? Next slide, please. Okay, so now we have finished one set of reactions where the carbonyl compounds were being reacted with strong nucleophiles and the reaction could take place in absence of an acid catalyst. The second set of reaction where the reaction is taking place with a weak nucleophile, and all these reactions I told you will be catalyzed by acid. Okay? So the first example that I've taken here is the reaction of an aldehyde or a ketone with a primary amine. Okay? Which is catalyzed by mild acid. It will lead to formation of first a carbinol amine. Again, what is happening is hydrogen adding on to the oxygen and the remaining group adds on to the carbon here. That is what has happened here. Right? You remember I told you, you have a carbonyl group. It will first add on proton. So what is happening here is you will have the electropositive carbon being generated and then it will add on the amine. A carbinol amine being formed. Now these compounds are not stable. In the acidic medium, what will happen? You will again have the dehydration reaction taking place. You can see first the protonation has taken place here. Once the carbinol amine is formed, the protonation will take place followed by a dehydration reaction. And what has happened in this reaction is we started with a carbon oxygen double bond. Okay? And see what do you end up with? You end up with a carbon nitrogen double bond. So I told you all these reactions are reactions by which we are converting a compound having a carbon oxygen double bond to a compound which is having a carbon nitrogen double bond, right? पहले addition होता है, उसके बाद dehydration होता है to generate a carbon nitrogen double bond. Clear? The next slide. So the same mechanism I have shown here. So the acid catalyst takes place to form the carbinolamine, which then undergoes an acid catalyzed dehydration reaction. Right? The mechanism I have already shown you here. Okay? The acid catalyzed addition of amine to form carbinolamine, and this carbinolamine which is formed here will then undergo a dehydration reaction by this pathway, and it will give you a carbon nitrogen double bond being formed here. Right? Next slide. Now this table gives you a complete idea of all the different ammonia derivatives that you can use, and you can react these ammonia derivatives with carbonyl compounds to prepare different compounds having carbon nitrogen double bond. For example, if you start with primary amine, the product obtained will be called a Schiff's base. If you start with hydroxylamine, the product formed will be called an oxime. If you start with hydrazine, the product formed will be called a hydrazone. Similarly, if you start with phenylhydrazine, the product formed will be called a phenylhydrazone. And finally, if you start with semicarbazide, the product formed will be called a semicarbazone. In the next slide, we will show how these reactions are taking place with the carbonyl compound and how the products are being formed. So you can see here, this is the reaction here. You have a ketone which is reacting with hydroxylamine, and it is forming the corresponding oxime. Can you see here, please? Now, how to write the product? To write the product, what you have to do is simply remove this oxygen and remove this hydrogen, and you attach this carbon to this nitrogen, and you will get the product. Right? Mechanism we have already discussed how it takes place. That is the product which is formed. It will be called the benzaldehyde oxime. It is an oxime which is formed by reaction of benzaldehyde with, what is this compound called? This compound is called hydroxylamine. Okay? Similarly, if I react benzaldehyde with Brady's reagent, it is called, this is 2,4-dinitrophenylhydrazine. Then again, to write the product, remove this hydrogen, remove this oxygen, and join the carbon with the nitrogen, right? And the product formed will be okay, and this product will be called 2,4-dinitrophenylhydrazone. 2,4-dinitrophenylhydrazine is the reagent. The product formed will be called 2,4-dinitrophenylhydrazone. Okay? So this is a benzaldehyde 2,4-dinitrophenylhydrazone being formed here. All right? Okay? And one last reaction which I want to show you here is the reaction with semicarbazide. Now, important thing that you have to understand here is semicarbazide mein there is this one nitrogen here and there is this one nitrogen here. Which is more nucleophilic nitrogen? That means which of the two nitrogens will attack? That we have to understand. Okay? When you react with semicarbazide, find that this nitrogen is more nucleophilic as because of the minus I effect. What will happen is the lone pair of electrons on this nitrogen get delocalized onto the carbonyl carbon. So they are not available for donation. That is why the nucleophilic attack will take place through this nitrogen. And the same way we have to write the reaction, remove this hydrogen, remove this oxygen and join the carbon to the nitrogen, right? So the reagent used here is a semicarbazide and the product formed will be called a semicarbazone. This is benzaldehyde semicarbazone being formed. Is that okay? Now, one last thing which I want to discuss here before I take up the questions on this topic is the role of pH. The role of pH in the nucleophilic addition elimination reaction. Please remember that reaction of all the carbonyl compounds with these ammonia derivatives takes place at a pH of 3.5 and that pH is very, very important. What is the role of pH in this reaction? See, I told you how the reaction takes place. The reaction takes place first by protonation. Okay? So the role of acid is very important. Acid is increasing the electropositivity of the carbonyl carbon, right? So you will. So if the medium is not acidic, then this protonation reaction will not take place. And if this protonation does not take place, then the weakly nucleophilic ammonia derivative will not be able to attack this carbon center. Okay? So role of acid is important. Now what will happen if the concentration of acid is higher than, like the pH is lower than 3.5, then what will happen? If the concentration of the acid is very high, then what will happen? If the concentration of acid is very high, then besides the protonation of this oxygen, this nitrogen will also get protonated. So in a strongly acidic medium, that means at pH lower than 3.5, what will happen is now if the nitrogen gets protonated, it will no longer be nucleophilic. So the nucleophilic attack cannot take place. There will be no nucleophilic addition reaction taking place. Right? Clear or not? So you require a pH of 3.5 to protonate oxygen. pH is lower than that, nitrogen also gets protonated. If nitrogen is protonated, the ammonia derivative will no longer be nucleophilic and you will not have nucleophilic addition reaction taking place. What if the medium is highly alkaline? The pH is very high. What will happen? एक तो ये प्रोटोनेशन ही नहीं होगा, ठीक है, प्रोटोनेशन नहीं होगा ना, तो कार्बन पे पॉजिटिव चार्ज नहीं आएगा. The other thing is you will have, that means at high pH the concentration of OH minus will be high. So if OH minus its concentration is high, what will happen? The OH minus can also attack the carbonyl center. ठीक है? So that is why it is very important that you maintain the pH at 3.5 for the ammonia derivative to condense and form the corresponding carbon nitrogen double bond. Clear? I have a small video to show you where I will show you how the nucleophilic addition reaction takes place on a carbonyl compound. ठीक है? पीछे पीछे. एक मिनट रुकना. So you can see here, this is the nucleophile, okay, and this is your carbonyl compound. This nucleophile will add on to this carbonyl compound, and this is our target compound, the addition product. Now let us see how the nucleophile attacks this carbonyl center. Please watch this carbon where the nucleophile is going to attack. See here. This is the carbonyl center, the nucleophile. It can either attack from the top or it can attack from the bottom. From either side it can attack. You see. थोड़ा सा पीछे चलेंगे. थोड़ा सा पीछे चलेंगे इसको. और थोड़ा पीछे. ये देखो. यहाँ पे एक बार देखो. See, now the nucleophile has attacked on the carbonyl center and the pi electron charge gets delocalized. ठीक है? So watch what will happen when the nucleophile comes from the top. These alkyl groups will be pushed down. See, watch now. Stop. See what has happened now? The nucleophile has attacked, and you have a four-membered product being formed. You have an oxygen with a negative charge. This oxygen with a negative charge now will take up a proton from the solvent, right? See, the proton has now got bound to the oxygen, and you have got a four-membered addition product being formed, right? So that is how the nucleophilic addition reaction on a carbonyl carbon takes place. Okay? So with this, we have finished what the today's part of discussion for nucleophilic addition and nucleophilic elimination reaction. So what we will do is now we will take up some questions. Okay? Next slide. So let us see the first question. It says, what happens when acetone is treated with excess of ethanol in presence of hydrochloric acid? Please write the reaction. The reaction of acetone What is this reaction? We have studied this reaction. What happens when carbonyl compounds combine with alcohols? They form dialkoxy compound is formed. Two OR groups get attached to the carbon, right? The ketal formation takes place, right? So the product formed will be, these are two groups already attached to the carbon, and then OC2H5. Two OC2H5 groups get attached to the carbon, and the compound formed will be a ketal. Ketal will be formed. ठीक है? We'll go to question 4. Question 2 and 3 we will do in the next class because one part of that reaction we have not done today. So that we will do in the next class. We will concentrate on question number 4. It says 2,2,6 trimethyl cyclohexanone does not show HCN addition reaction. Please write the product reactant. 2,2,6 trimethyl cyclohexanone. This is the compound 2,2,6 trimethyl cyclohexanone, right? Why it will not show addition reaction with HCN? क्या फैक्टर्स हैं जो न्यूक्लियोफिलिक एडिशन रिएक्शन को डिटरमिन करते हैं? Steric hindrance, है ना? So you can see here that you have, in this case, there are 3 methyl groups which are adjacent to this carbonyl carbon. So the attack of this cyanide ion will be sterically hindered. So because of steric hindrance, (2,2,6) trimethyl cyclohexanone will not show addition reaction with HCN. ठीक है? Next. The next reaction is to convert acetaldehyde to butane 2-one. Now aldehyde से तो हमने कोई सिंथेसिस नहीं पढ़ा कार्बोनिल कंपाउंड का, कीटोन का, बट एसिड से कर सकते हैं. What will happen if I oxidize it? कार्बोक्सिलिक एसिड बन गया ना. Now if I react with PCl5, I can convert it into acid chloride. अब कर सकते हैं आप. एक बार acid chloride बन गया, so how will you convert this now? You react this with what? Gilman's reagent. You react it with diethyl cadmium and you can convert it into the corresponding ketone. ठीक है? The next reaction is to convert propanol. You have to convert propanol to propanone. देखो प्लीज रिमेंबर, प्राइमरी अल्कोहल है, अगर हम उसको ऑक्सीडाइज करेंगे तो क्या मिलेगा? Primary alcohols on oxidation give you aldehyde. And how are ketones obtained on oxidation? Secondary alcohol. So if I can somehow convert this 1 propanol to 2 propanol, okay, then I can convert this by oxidation reaction. So how will I convert 1 propanol to 2 propanol? You have done in alcohol chemistry. Dehydration कर दो इसका, right? You do the dehydration reaction. You heat with concentrated sulfuric acid, it will undergo dehydration reaction and the product formed will be a alkene, ठीक है? And now, if you do the hydration reaction, the addition will take place in accordance with Markovnikov's rule, and the product obtained will be no 2-degree alcohol. You will get isopropanol being formed. Water molecule will add in accordance with the Markovnikov rule. So hydrogen adds here and OH adds here, right? When that reaction happens, you will get isopropanol being formed. अब इसको oxidize कर दो. What is the oxidizing agent? Secondary alcohol. The oxidizing agent used will be so many we have learned. PCC. You can use PCC. You can use PDC. You can use Collins reagent. है ना? To convert the secondary alcohol to ketone, right? Clear? Okay. The next reaction, please. Benzene to benzophenone. This is very easy, only one-step reaction. We have done this reaction. So how do you convert benzene to aromatic hydrocarbons to aromatic ketones? What is that reaction we have learned? That reaction is? What is the name of that reaction? Fiedel-Crafts acylation reaction, right? So you reacted with what? You reacted with benzoyl chloride in presence of AlCl3 as the catalyst, and you will get benzophenone. ठीक है? Correct? Next is conversion of acetic acid to 2-pentanone. Now this should be easy. Once we have done that first reaction, we should be able to do this. So what do we do first? First, convert acetic acid to? Good. We converted into acid chloride. You reacted with PCl5, converted into acid chloride, and then reacted with how do you convert acid chloride to ketone? By reaction with? Yes, by reaction with Gilman's reagent. Okay? So we have converted acid chloride to this is pentanone, तो एक कार्बन और होना चाहिए ना बच्चे, right? तो 3 कार्बन लेना पड़ेगा हमारे को. So instead of using diethyl cadmium, we will use dipropyl cadmium. Okay, that 1 carbon we have missed. The last reaction is to convert acetic acid to ethanol. Now this should be very easy. There's one name reaction we have learned. See, acid से तो या तो आप ये कर सकते हैं, you can start with calcium acetate, and you reflux it with calcium formate. But again, in that case, you get mixture of products. So it is not a very good reaction we have learned. Okay? There is one more reaction, some name reactions we have learned to prepare aldehyde. What will happen if I convert it into acid chloride? Can you now convert it into what is that reaction we have learned? That reaction is the name reaction we have done to convert acid chlorides to corresponding aldehyde. Rosenmund reduction, yes. So you react it with hydrogen in palladium, which is precipitated on barium sulfate. Yes. हाँ बेटा. इथेनॉल ही तो है वो. इथेनॉल ही तो है बेटा, है ना? Acetaldehyde is ethanol. ठीक है ना? So you have, what we have done is you have converted acid chloride to ethanol or acetaldehyde. That is the common name. All right. Now can you tell me what is the role of sulfur here? Why do you need to poison the catalyst? What is the role of poisoning the catalyst? Yes, that is to prevent, no, not carboxylic acid, beta, reducing medium hai na. So then what will happen is, if the catalyst is not poisoned, aldehyde will get reduced to alcohol. Okay? So the poisoning of the catalyst will prevent the further reduction of aldehydes to alcohols. Okay? Any questions you have or that you want to answer, ask? Any question in particular that you want to ask? Okay, yeah. So let's do that 6th question. Now, in the first part, I have given you these 4 compounds. Okay? You have to arrange them in the increasing order of nucleophilic addition reaction. Let us write these compounds first. Butanone, propanol, propanone and ethanol hai beta. Right? So now, how will you arrange them in the increasing order of nucleophilic addition reaction? Correct? The order will be and how do you explain this order? What is the reason for the order in this? Exactly. Now, in case of ketones, you have 2 alkyl groups. Here you have a methyl group and you have an ethyl group. Ethyl group is more bulkier, okay? As compared to, you have 2 alkyl groups here also. But the ethyl group is more bulkier as compared to methyl group. So there is a greater steric hindrance here to a nucleophilic addition reaction, right? So 2-butanone will be less reactive than propanone, and then which has 2 methyl groups which are offering inductive effect and then steric factor. In case of propanol, you have one alkyl group and you have one hydrogen, right? So the reactivity of propanol will be more than acetone because one bulky alkyl group has been replaced by a small size hydrogen atom, right? And finally, when we go to acetaldehyde or ethanol, again a slightly bigger ethyl group has been replaced by a smaller methyl group. So the steric factor here will be less as that compared in the propanol. That is why the nucleophilic addition reaction will be faster in ethanol as compared to that in propanol. Okay? The next part of the question is, if you have acetophenone okay, and if you have para-tolualdehyde, then you have para-nitrobenzaldehyde, and the other one is benzaldehyde. Please try to arrange them in the increasing order of nucleophilic addition reaction. Para-nitrobenzaldehyde. देखो पहले तो आप सबसे पहले एल्डिहाइड्स को कीटोन से सेपरेट कर लो, ठीक है? We know ketones are less reactive than aldehydes towards nucleophilic addition reaction. So इन चारों में से कितने कीटोन्स हैं आपके पास? कीटोन तो एक ही है बेटा, कीटोन तो एक ही है ना. So that means what is that compound? Ketone? Acetophenone, है ना? That means acetophenone will be least reactive towards nucleophilic addition reaction. ठीक है? अब उसके बाद और तीन कंपाउंड रह गए. एक para-tolualdehyde है, दूसरा para-nitrobenzaldehyde है और थर्ड है benzaldehyde. ठीक है? Now एक चीज you have to understand. We said that the low reactivity of aromatic aldehydes or ketones towards nucleophilic addition reaction is because benzene offers a plus R effect. It is giving its electron pair to the carbonyl carbon and it is decreasing the electropositivity of that carbonyl carbon, right? Number one. And number two we said is because benzene ring is bulkier. Okay? So it is offering a steric hindrance. That is why the reactivity of aromatic aldehydes is lower than that of the aliphatic aldehyde. Now, when you have a group attached to benzene ring, which is electron donating, so that electron donating group is going to increase the electron donating tendency of the ring. So benzene ring will be a better electron donor when there is an electron donating group attached to it, right? So what is the electron donating group that is attached to benzene ring here? Methyl group here, okay? Which is donating electrons onto the ring, whereby increasing the electron charge donating tendency of the benzene ring. The other type of substituent which is attached to the benzene ring is a nitro group. And nitro group is what type of group? Nitro group is an electron withdrawing group. It withdraws electrons by what? It withdraws electrons by Nitro group withdraws electrons by two effects. What are those? It withdraws electrons by minus I as well as minus R, right? So when you have an electron withdrawing group attached to the benzene ring, it is going to decrease the electron donating tendency of the ring. If it is decreasing the electron donating, because what will happen is the pi electron cloud of the benzene ring will get delocalized onto the nitro group. So benzene ring can no longer donate electrons. If benzene ring cannot donate electrons, means the electropositivity of the carbonyl carbon will be higher. And if the electropositivity of the carbonyl carbon is higher, the rate of nucleophilic addition reaction will be high. Okay? So when you have an electron withdrawing group attached to the benzene ring, it will accelerate the rate of a nucleophilic addition reaction. And when you have an electron donating group attached to the benzene ring, it will deaccelerate the rate of a nucleophilic addition reaction. With that clarity, now tell me what will be the final increasing order of nucleophilic addition reaction in this case. Acetophenone. Very good. Very good. So the final order will be okay? Correct? Let's go on to the next question. Next slide. You have to identify the X and the Y in these reactions. In the first reaction, very good. In the first reaction, the X will be what? Let us see the second question. क्या reaction है बेटा ये? What reaction is this? This is ozonolysis reaction. So what happens in ozonolysis reaction? कार्बन कार्बन डबल बॉन्ड है, उसको आप क्लीव कर दो, ठीक है? तो क्लीवेज कर देंगे कार्बन कार्बन डबल बॉन्ड, और जो कार्बन हैं वो डबल बॉन्ड से अटैच्ड है, उनको हमें ऑक्सीजन से अटैच करना पड़ेगा, ठीक है? So please write the product. What will be the XX that you get here? साइक्लोपेंट कैसे हो गया? 6 है ना? दिस इज साइक्लोहेक्सीन. दिस इज साइक्लोहेक्सीन. So just cleave this double bond here and attach the oxygen. ठीक है. Clear? That will be the product you will get. The next reaction. This compound is butanol. First part of the reaction we have already done. It will react with ethanol in acid, and the product formed will be an acetal, right? Carbonyl compounds combined with 2 molecules of alcohol in the acidic medium to form acetal or ketal, right? Because you're using a ketone here, you will get a ketal. Okay. And what will happen then next? What is the next reaction? Yes. Next is the hydrolysis of ketone. Please, and I told you, if you remember, that if you have an acetal or a ketal, you can hydrolyze it back to the corresponding carbonyl compound by using a mild acid or an alkali, right? So if I react with mild acid or alkali, my product obtained will be this. Okay. I think that will be all for today. In the next class, we will learn the remaining reactions of aldehyde and
Hello students, as you know we are doing Maxima Minima. So today we'll just do a quick revision of the concepts and then take up the problems. Now, uh, like we have discussed these things, I'll ask you one by one about these concepts. Now you tell me about the critical points. What are critical points of a function? Either the first derivative is equal to 0 or the derivative does not exist. But if you read this definition, fx is a real valued function with domain D, some domain, and x equal to a is said to be a critical point in the domain if critical point in the domain if either the derivative at that point is 0, right, or the derivative does not exist. F dash a does not exist. But one important point you should note is that at that particular point where either the derivative is becoming 0 or our the derivative is not existing, the value of the function should exist. If the function does not exist at that point, in spite of the derivative not existing, it will cease to be, it will not be a critical point. So finally, what we conclude, a critical point x equal to a is said to be a critical point if either the derivative at a is 0, second, or the derivative at a is not existing. But you have to keep in mind that the value of the function at a should exist, right? We'll take up some questions in which you have to take care of this fact also. Now next is stationary point. Now who will tell me about stationary point? One student at a time. The derivative is equal to 0. We don't take into consideration the points where the derivative does not exist. So what is stationary point? See, the critical points include the stationary point. So stationary points are those where the derivative is becoming 0, right? The first derivative is becoming 0. That means it can be a point of local maxima, it can be a point of local minima, or it can be a point of inflection. Is that clear? Critical points and then stationary points. Now next is maximum or absolute maximum or global maximum. Now who will tell me what is absolute maximum? We have discussed this. Yesterday we have done this. What is absolute maximum or global maximum? That means global maximum is if value of the function at a is greater than equal to value of fx for every x belonging to the domain throughout. That is the absolute maximum. Like suppose there are three or four different sections in a school, and in each of the section a student will obviously take maximum marks. Now there are four sections and all of them have mathematics, and there are four different toppers in each of the sections. Like, so each of the student will say I have scored the maximum marks. Suppose their marks they have scored is 92, 95, 99 and 100 full marks. Then only one student can claim he is the absolute maximum. Which of the one who has scored the highest among the four sections can obviously claim he is the absolute maximum in that school, right? But if he has scored 100, he can claim that is the absolute maximum of the entire universe in which all the students who have appeared. So you have understood the difference, the absolute maximum and the local maximum. So a local maximum point can be a point of absolute maxima. So this concept, when we are talking of absolute maximum, there exists a point A. It is said to be a point of absolute maxima if value at A is greater than equal to the value of the function in the entire domain wherever it is defined. Is that clear? Now next comes similarly absolute minima. So in absolute minima, what you will do, you will just change the inequality. Instead of greater than equal to, you will write less than equal to. So if fa is less than equal to fx, where x is in the entire domain, then it is a point of absolute minima. It is also known as global minima, right? So these concepts I think are well placed, and now you understand them. Next, relative or local maxima minima. Now, what is relative or local maxima minima? Who will explain me what is relative or local maxima minima, and also how it is to be found, how we can differentiate between a point of local maxima from the point of local minima, and how can you find the point of inflection? Local maxima minima is also known as relative maxima minima. Now, what's the difference of between a relative local maxima minima and absolute maxima minima, and then how to find out how to differentiate between that at a particular point the function is a local maximum or a function is local minimum or it is a point of inflection, right? Local or relative. See, I have explained you this. First step is, what are the possible points of local maxima minima? Who will tell me the possible points of local maxima minima? Yeah, critical points. So how you will find critical points? We'll first find out the points where the derivative is 0. We'll get stationary points, and besides this, we'll also find the points where the derivative does not exist. That can also be a point of local maxima minima, right? So first step is you will find the critical points. And you remember we mentioned that the condition that f dash x is equal to 0 is necessary but not sufficient. Now, what is the meaning of necessary but not sufficient? Necessary means that at every point of local maxima minima, the value of the derivative, first derivative will vanish. It is necessary if it exists. If the derivative does not exist, then it is a different thing. If the value of the derivative is existing and it is a point of local maxima minima, then the value has to be 0. So at every point you can write, at every point of local maxima minima, at every point of local maxima minima, if first derivative exists, if f dash, you can write if f dash exists, the value is necessarily 0. This way it is necessary, or it may not exist. Like the classical example which you can take is mod x. The derivative is not existing, but you will have a local minima. So, but it is not sufficient means if other way around, if we are given that the value of the derivative is 0, with surety or with 100% surety, you cannot claim that the particular point has to be a point of local maxima minima. So we say it is a necessary condition, but it is not sufficient. Now this is clear to you. Now how to differentiate between a point of local maxima from the point of local minima and from the point of inflection using the first derivative test? See, this is local maxima and this is local minima relative to some axis. I am taking this is x-axis, y-axis, origin, x-axis, y-axis, origin, right? Now you tell me, one of you, what about a point? Let us say this is a point x equal to a, and in this case you can just make out it is a point of local maxima because it is taking the maximum value. See, the definition is same. Fa is greater than equal to what? Fa is greater than equal to fx, right? Where x lies? Yeah, you can say fx, fa is greater than equal to fx, where x belongs to, yeah. So, and where what is h? A positive quantity and tending to 0. So this is a point of, we claim x equal to a is a point of local maxima. Now, how to find out? With the help of the sign of the first derivative. In case of local maxima, what will happen? See, if you observe on the left hand side, the function is increasing. The function is increasing. Now, if the function is increasing, you draw a tangent, it will make an acute angle. It will make an acute angle with the positive direction of x-axis. This angle is acute, less than 90. So what is tan theta here? Positive. So that is, and tan theta is what? Slope of the tangent is nothing but it is equal to the first derivative. So first derivative will be positive here. And when you cross it, we are not finding the second derivative. We are just finding out the first derivative and see how the curvature, because the curvature of the curve will change and the derivative will change sign from positive to negative. See, if you extend this angle will be what? Obtuse. So the derivative will change sign from positive to negative, and at the highest point where this peak is formed, the curvature will change, right? From increasing, it will change to decreasing. It will change from increasing to decreasing, right? So at this particular point, the derivative will be 0. So the first derivative will change sign from positive to negative as we'll cross the point x equal to a from left hand side to right hand side in case of a point of local maxima, right? And the reverse will happen in case of point of local minima. What will happen in this case? This is a point of local minima. If on the left hand side the function is decreasing, it will attain a minimum value and then it will start increasing. So what is happening on the left? Since it is decreasing, the derivative is negative, and now it increases, it is positive, and at this point the derivative is 0, right? This is about the sign of what? First derivative, f dash x, right? And in case of inflection, what happens? The sign of, yeah, the sign will not change. Remember this. If you take x cube, the graph is like this. Fx is x cube. So it is increasing on the left, then again it increases on the right of origin. At the origin, the value of the derivative is 0. The tangent is there. The x-axis is the tangent. But on the left hand side, the function is increasing, and on the right hand side also the function is increasing. So the derivative will not change sign. The derivative will remain from positive to positive, or it can be from negative to, you can consider this curve, right? What is this curve? Y equal to what? Think about it. So this is the case when I am taking the sign will not, it will be same, negative to negative, because the function decreases. And what you will notice is at the point of inflection, if you draw a tangent, some part will be below it and some part will be above it. And the second derivative at the point of inflection will be what? If you want to find, see, you can just think, but the second derivative will be 0. The second derivative will be 0. Because what is second derivative? Derivative of first derivative. So rate of change of slope. Rate of change of slope. If you consider this function fx is equal to x cube, you find the first derivative. What is the first derivative? 3x square. If you draw the shape of 3x square, what it will look like? See. See, you will notice few more facts. You draw the graph of x cube, and in the same graph, you draw the graph of y equal to 3x square. Just draw both of them on the same axis. Some water. See. This is x square. This is fx is x cube, and this is fx is x square. X square will be like this, right? So what is the value of second derivative at the point of inflection? 0. And you will also notice that at the point of inflection is the point of minima in this case. See, you draw the curve of y equal to x cube, right? You find the derivative. Derivative will be 3x square, right? Derivative will be 3x square. But the shape will not change much. Maybe the values will be greater 3 times. The values will become greater, right? But then you have to be careful which curve will come above and which curve will come below, because now it is 3x square. The curves may change. But one thing is sure, that the point of inflection is the minimum point in the graph of the first derivative. Is that clear to you? So the first derivative does not change the sign, and the sign of the second derivative will be 0, and the sign of the third derivative will be non-zero. Or some odd derivative may vanish, or some odd derivative may vanish. See, in this case, this was the first derivative, right? What is the second derivative? No, see, we'll just write it again. The function was what? X cube, right? First derivative, 3x square. Second derivative, 6x. Third derivative, 6. Now at 0, what is happening? 0. Value of the function we are not interested in, but first derivative is becoming 0. Second derivative, so second derivative is 0. And what about the third derivative? Is positive. Now is that clear to all of you? Right? Now next. First derivative test we have done. Extreme values are either points of local maxima or points of local minima. This we have done. Just next, please. Now second derivative test, right? Now second derivative test. X equal to A is a point of local maxima. X equal to A is a point of local maxima when first derivative is 0. And what about second derivative? Second derivative is negative. Is that clear? And you know, second derivative gives us the concavity and convexity of the curve. You should be clear about this. Like, see, if you have a function, a simple function fx is equal to x square, right? What is the first derivative? 2x. Second derivative? 2. It is positive. Now, what can you claim? If the second derivative is positive, in for this particular curve, the graph of y equal to x square is this, right? Yeah, second derivative minima is 0. Minima at 0 is there. But if the second derivative is positive, it will be concave from above. Remember this. It will be concave from above. It is increasing function when x is positive. When x is positive, it is increasing. When x is negative, it is decreasing. Now, since the first derivative at 0 is 0 and the second derivative is negative, therefore, second derivative is what? No, in this case, second derivative is positive. So it is a point of local minima. But what I was trying to tell you was, if you find the first derivative and the second derivative, if the second derivative is positive, it is concave from above. Like if you consider this function y equal to log x. What is the first derivative? 1 by x. Now you know log x is defined only when x is positive. Now what is the second derivative here? Now this is negative. So what can you say about its concavity? The shape of log x is like this. It is asymptotic. It will not touch. It will come closer and closer, right? This is y-axis. This is x-axis. So it is concave from below or convex up. It is also known as convex up. Is this concept clear to you? Huh? Because the sign of the second derivative tells you the concavity or convexity. That is the reason. See, when second derivative is coming out to be negative, why it is a point of local maxima? When second derivative is negative, the shape is like this. It is when second derivative is negative, the shape is concave below. And when it is concave below, you will have a point of maxima. If you want to understand this, you have to learn what is second derivative. Second derivative is the rate of change of first derivative. So when you will find out the rate of change of first derivative, you will find that the shape is to be like this, right? You have to first find out the slope and then you have to differentiate the slope. This is the derivative of the slope and the derivative of the slope will be like this. And if it is a point of local minima, instead of local maxima, if it is a point of local minima, then what is second derivative? It is positive. Like in case of fx is equal to x square. Next. Point of inflection is clear. Nth derivative test, who will tell me? One of you tell me the nth derivative test. If suppose the first derivative is 0, right? Second is positive, negative, we get, positive we get local minima, negative we get local maxima. Now, if the second derivative is 0 and we want to go to further derivatives, then how you will find out whether it is a point of local maxima or minima? All even? No. All derivative, if any even derivative, instead of second, you take the fourth. Instead of fourth, you take the sixth. If any even derivative is positive, then it is a point of local minima. If any even derivative is negative, it is a point of local maxima. But all derivatives prior to that should vanish, right? And if any odd is positive or negative, then it is neither local maxima nor local minima, as we have seen in case of point of inflection. Now properties we have discussed already. Next, please. Yeah, these questions we have done. I think we were on 14th. First few questions we had discussed. Fourteenth. 11th. Let us. I think we were discussing these. 11th, you try. 11th, we left at 11th, and I told you what to do. They are extreme points. So at -1, the value of the derivative should vanish, and it should also vanish at 2. You solve it and tell me what are the exact values of A and B. I think B is not correct. I said I think B option is correct, but it is the C option. You just find out. What you have to do is, in place of x, you put, first you find the derivative. You first find the derivative, and then you substitute x equal to -1, and then you substitute x equal to 2, and solve the two equations and see what the result is. I think alpha is coming out to be 2. Beta minus half. So C is the correct option. There's another question similar to this. You can write down fx is a log x. Fx is a log x plus bx square plus x. And the two extremas are at 1 and 3. At 1 and 3. The function is same. Fx is equal to a log x plus bx square plus x. So whenever points of extremas are given to you, you find the derivative and equate it equal to 0. So the derivative will be a by x plus 2bx plus 1. Right? Now what you do is substitute 1. So this gives you a plus 2b plus 1 equal to 0. Right? And then substitute 3. A by 3 plus, if you put 3, 6c plus 1 equal to 0. Now you solve these. This will give you a plus 2b is equal to -1. Right? If you multiply by 3, what you will get here? A plus 18b is equal to -3. Now subtracting these two equations, minus 16b is equal to 2. See, you change the sign, right? 2 minus 18. So b is equal to -1 by 8. And this value of b you will substitute in any one of them. You can substitute in this. So what you will get? A is equal to -1 minus twice of b. B is -1 by 8. So this will be -1 minus 3 by 4. Now try the next one. The total number of local maxima and local minima for this function you have to find. How many points of local maxima and minima are there? See, we don't have to find the local maxima or minimum value. Neither we have to find the value nor the points. How many points we have to find out? See, it is piecewise defined. For -3 to -1, it is semi-open, right? From -3 is not included, but that will not make any difference. So -3 to -1, you have 2 plus x whole cube. And when x is greater than -1 and less than 2, the value is x raised to the power 2 by 3. Now you have to find out how many points of local maximum minima are there. And see, you have to find the critical points. You have to find the critical points if they exist. Because the critical points can also be points of local maxima minima. Just finding derivative and equating equal to 0 will not solve the purpose. Only one point. And what is that point? See, you can either you can do it algebraically or you can do it graphically also. The other day, yesterday, I was discussing about graphs can help you to understand the shape of the curve, and then you can easily visualize which are the points of local maxima minima. See, I'll do it both ways, right? And then you can adopt any one of them. All of you have tried? See, fx is equal to 2 plus x whole cube. And what is the interval? -3, -1. Now, if you draw the graph of this is x-axis, this is y-axis. What will be the shape of 2 plus x whole cube? Obviously, it will not pass through origin. If you draw x cube, the shape is like this. Had it been x cube, tab to the shape would have been this. Now, when in place of x, you are incrementing it by 2, you are adding 2 to it, then what will happen? The curve will shift to the rightwards or leftwards. See, now at -2, the value will become 0. So the -2, the point -2 will act as origin. So the origin will shift. If you add 2, the origin will shift 2 units to the left. And if you subtract 2, the origin will shift 2 units to the right. So these curves, see, very simply, if you all of us know graph of y equal to x cube. Now adding 2 will shift the curve to 2 units to the left. Adding, it shifts to the left. Subtracting, it shifts to the right. So the shape will be like this. See. So suppose we consider this as -2. This will be the shape. And we have to consider it till -3. Let us say this is the point -3. And this point is open. Open point, you understand? Right? Not included. And what will be the value at -1? Till -1 we have to draw, not beyond this. So if you substitute -1 here in this, the value is 1. So the shape will be slightly, it will be like this. Right? So let us say this value is 1. If you substitute -1 here, so it is 1. So we have drawn from -3 to -1. And from -1 to 2, you have x raised to power 2 by 3. Now you try this. What will be the shape of x raised to power 2 by 3 between -1 and 2? Right? I can erase this part. This is the origin, right? And what points you have to take? -1 to 2. Till 2 we have to draw. Anybody who has drawn? the shape of x raised to power 2 by 3 between -1 and 2? What is the shape? Show me the shape. Anyone who has drawn it? See, one thing is for sure, x raised to power 2 by 3 will not go below x-axis because it is square of the cube root. It is square of the cube root. Cube root can be negative, right? But when you will square it, it will be positive. So it will always lie above the x-axis, and value at 0 will be 0, right? What else? Rough sketch we want. But see, certain things will help you to draw the graph. If you consider fx is equal to x raised to power 2 by 3, this is in what interval? -1 to 2, right? Now, first derivative is what? 2 by 3 x raised to power -1 by 3, which is 2 by 3 x raised to power 1 by 3. So 0, the derivative is not existing. At x equal to 0, the denominator is becoming 0. So the value of this expression, the first derivative does not exist at 0. So it is a critical point and the derivative does not exist. So derivative does not exist geometrically means what? The derivative not existing at 0 means what? Geometrically, there will be a sharp point. The curve will not be smooth at the origin. So there will be a sharp point. Now, see, this will be the shape. And how can you say this is the shape and not like this? See, the curve can be like this also. How can you differentiate? How can you make out this shape is correct? See, if you find the second derivative, if you find the second derivative is 2 by 3 multiplied by -1 by 3, x raised to power -1 by 3 minus 1 is -4 by 3. So it is coming out to be negative. See, this is coming out to be because of this, right? This will always be positive. This is a positive quantity because it is -2 by 9 x raised to the power 4 by 3. Because of this 4, this will be positive. But because this sign is minus, so this is negative. So negative means it is concave downwards, concave from below. You're getting my point? When I explain to you it is concave from below, because the second derivative is negative, the shape will be like this. So these standard curves, you can just remember the shape. Every time you don't have to draw. Once you know the graph of y equal to x raised to power 2 by 3, then you can draw it in one go, right? Here you are being explained, so it is taking more time. But when you are familiar with this method can save time. Now what about this? At 1 also the value will be 1 and it will go like this, somewhat like this, right? At 2 is open, yeah, right? Now you look at this. Now we have the graph of this function. Fx is equal to 2 plus x cube in that particular interval from -3 to -1, and then x equal to 2 by 3. Now how many points of local maximum minima are there? See, is this a point of local maxima? This point? This is a point of local maxima. Not because the tangent is parallel. You cannot have a unique tangent at this point. Unique tangent is not there. You're getting my point? At this point, it is a critical point where the first derivative does not exist. But it is a sharp point. But it is a point of local maxima because you see the change of sign. On the left, the derivative is positive, and on the right, the derivative is negative. You can just see, if you are doing it algebraically, you can how you will notice. Suppose the curve is not there, you don't draw the graph. Then what is the way out? Then the algebraic equivalent is find the first derivative, right? Equate it equal to 0. What is the point? -2. First I am finding the first derivative. First derivative is this. I equate it equal to 0. I get -2. So now there is some hope, or some students will think this is a point of local maximum minima. But then if you see the change of sign, on the left if you substitute a value slightly less than -2, the first derivative will come out to be positive. And if you take a value slightly greater than -2, like -1.9, if you substitute -1.9 here, because of square, this is positive. So derivative is changing sign from positive to positive. So this point which we got is not a point of maxima, or neither point of maxima nor a point of minima. So this is ruled out. Now take this. The derivative is here. If you equate it equal to 0, I don't get any point. So we don't get any point by equating the first derivative equal to 0. We don't get any point. So now what else we have to check? We have to check for other critical points where the derivative does not exist. In this case, derivative is existing at all points. There is no point where the derivative will not be existing. And in this particular curve, if you consider 0, at 0, the derivative does not exist. So one point is 0, where the derivative does not exist, and it is a point of local minima. The other point is this, where the order relation is changing, where one curve ends and the other start. And at this point, you have to find out what is the nature of the graph. Or algebraically, you can make out that the sign change of sign is from positive to negative. Therefore, it is a point of maxima. So, is that clear? So, the right answer is see, I have taken so long to explain this graph. If there is any problem, is somebody on the online? Acha, now your question is, can you explain the graph again? Now, what you have not understood in the graph, you can specifically ask me what you want to know. See, this is a combination of two graphs. One is 2 plus x whole cube. This is a cubic curve. It will have a point of inflection. And since you are adding 2, it will shift 2 units to the left. So this is the shape of y equal to x cube. By adding 2, it shifts to the left, right? So this is just like x cube, the first function. First function y equal to 2 plus x whole cube is just like y equal to x cube. See, the shape of y equal to x cube is this, right? So what will happen? It shifts to the left. So this is the first part. The second one is x raised to the power 2 by 3. Now x raised to the power 2 by 3, x raised to the power 2 by 3 is fx is x raised to the power 2 by 3. What is this? Cube root of x square, right? So you have x square, this is x square, right? And when you will take cube root, what will happen? For values which are less than 1, at 1 the value will be 1. When x square is 1, the value will be 1 for both sides. And when x square is greater than 1, the values will be what? Both. See, it will not go below the x-axis. One thing is for sure. So cube root values when x is greater than 1 will be slightly less than x square, the value of x square. So the shape will be like this. So these two curves can be drawn like this. First is y equal to 2 plus x whole cube, and the other one is x raised to the power 2 by 3. Now is that all right? Next question, please. So the right answer is 2. Now this one, f, g and h be real valued functions defined on the interval 0 to 1, this interval. And these are the three functions. Fx is e raised to the power x square plus e raised to the power minus x square. Gx is xe x square plus e raised to the power minus x square, and hx as written here. If ABC denote the absolute maximum of f, g, h in the interval 0, 1, f is ABC are their absolute maximums, then which of the conditions is true? A, B are equal, A, C are equal and A and B are different? A is different from B and C is different from B, or all three are equal? Find out. There are three functions. Actually, what you have to do is you have to find the maximum value for each of the three functions in the interval 0, 1. We are just concerned in the closed interval 0, 1. And then that value is A, B, and C for the three functions. You have to find the relation between A, B, and C. You take the first function, e raised to power x square plus e raised to power minus x square, and find out the derivative and see what is its behavior. What is the point of maxima? Absolute maxima we have to consider. So when we have to consider absolute maxima, we have to take the endpoints as well, because it is a closed interval. So what we do to find the point of absolute maxima? First thing, we find the derivative and equate it equal to 0, right? Or other critical point. Second, what we do? We find the value of the function at the critical points as well as the endpoints. And then we write them in tabular form and find the value of the function. And then you compare the one which is the greatest is the absolute maxima. The one which is the least, smallest is the absolute minima. But the interval is 0, 1, right? Go ahead with it. See, again, you can do it either algebraically or with the help of a graph. Graphically also you can somehow crack these problems. But until unless you have that understanding of how to draw the shapes of the graphs, then it will take a long time. So initially, just to make you understand, I'll explain you these curves also, how to draw it graphically, how to solve the problem algebraically also. But then once you have understood the graphs, then you can, by practice, you can do them fast. See, if you consider the first function, fx is equal to, this is 13th problem, fx is equal to e raised to power x square plus e raised to the power minus x square, right? Now I have to find the points of absolute maxima. I am finding out the derivative and equating it equal to 0. So what is the derivative? Right? Now, if I take 2x common, I'll be left with e raised to power x square minus 1 upon e raised to power x square. Right? Now, can you claim this is positive? If I make a claim this is positive, you agree or not? So if the first derivative is positive, then what it means? It is an increasing function, right? It is an increasing function, and see the domain from 0 to 1. X is positive. X is positive. So when x is positive, this will be positive. This will be positive. Therefore, it is an increasing function. And if you are still not convinced that this will be positive, see x is positive because the interval is 0 to 1. 0 to 1, it will be positive. You leave side 0. In the open interval, it will be strictly positive, right? At 0, the value will be 0. Now, if you consider this function as gx, e raised to power x square minus 1 upon e raised to power x square, and find the derivative of this function. 2x e raised to power x square, and this will be what? The differential? Yeah, this was the first derivative. You can write it like this, minus e raised to power minus x square. And when you will differentiate, this will be plus 2x e raised to power x square, right? See, I am considering this function as gx, and I am differentiating it. Now, when I am differentiating it, what is this? Will this be positive or not? In open interval 0, 1. At 0, the value will be 0. Now, g dash x is positive means what? Here you can say with conviction, because the negative sign is not there in between, that this is positive. Here still you had some doubt. This is positive. So that means g dash x is positive. That means gx is an increasing function. Now, if this function, this was gx. Now, if this is an increasing function, then we can claim that gx will be greater than equal to g0 in the interval 0, 1, because 0 was the smallest point. This is what is increasing function. If a function is increasing, then gx will be greater than or equal to g0, where x is any point in this. X is any point in the domain 0 and 1, right? In the open interval. So, what is gx? E raised to power x square minus 1 by e raised to power x square is greater than what is g0? G0 will be 0 only. So, what we have concluded, this is positive. So, similarly, you can show that all the curves are increasing. All the curves are increasing. All three. So, the maximum, the greatest value will occur at what point? 1. See, if in this interval, if the function is increasing in some interval, right? So the greatest value will occur at strictly increasing, then the value, greatest value will be at 1. So you find the values at 1. Find the values of these three functions at x equal to 1 and then compare them. Right? What is the value at 1? A is value at 1 because we have found out that the functions are increasing, strictly increasing. So the maximum value will be at 1. So value at 1 here is 1 plus 1, 2. What is the value at 1 for the function gx? No, it is not coming out to be 2. It is e raised to the power 1. E plus 1 by e, right? It is e plus 1 by e. Now similarly for the second, if you substitute 1, e plus 1 by e. And for the third, e plus 1 by e. So now, so what is the right answer? A is equal to B is equal to C. Is that clear to you? See, algebraically also, graphically you can just make out why it is so. See, what is the graph of the function e raised to power x? Or can you tell me what will be e raised to power x squared like? Rough sketch. 0 per the value will be 1, right? What is the shape of e raised to power x squared? What is the value at 0? 1. This particular curve, right? And what will be the value at 1? E. E is 2.718. 2.7 will be, this is 2, this is 3. So it will be like this. We have to draw till this point. Let us say this is a point 1. So this is 2.71 roughly, right? This is E. This is the shape of e raised to power x square. And what is the shape of e raised to power minus x square? The value at 0 will again be 1. Actually, when you will draw the graph of this, you will realize it will start from 1, but it will come down like this, asymptotic, right? Now, if you find their sum, you find the sum. So what is twice of this? It will start from here, right? And it will, yeah, it will go up like this. You're getting my point. Now in this curve, I am adding this distance, this. So if this becomes twice. Now to this, if I add this, I go that many units above, right? So the shape will be like this. So it is, you can make out it is strictly increasing. This is the sum. This is the function fx. It is strictly increasing. So the highest value will be at 1. And you substitute 1 and you obtain. 14th question you try. Now 14th question, you will find that all the indices are, the powers of the variable x is even. Find the derivative. Find the derivative and equate it equal to 0. You will find out the points of local maxima or minima. Px is equal to A naught. This is an examination problem. This has been asked. A1 x square, A2 x4, and finally An x raised to power 2n. This is relatively simple. You just first try it out. I'll give you some time. Find out the points where the function is having relative maxima or minima. Only one maxima, only one minima, only one maxima and one minima, or neither a local maximum nor a minimum. Local will also be absolute in this case. Local will also be absolute. So you just find the derivative and equate it equal to 0 because this closed interval is not there. So the only point where it will be maxima minima is where the first derivative is 0 and the change of sign will tell us whether it is local maxima or local minima. Find the first derivative. P dash x is equal to A0 derivative is 0, 2a1x plus 4a2x cube plus 2n an x raised to the power 2n minus 1. Now when this will be 0? X equal to? See, if you take x common, you will find you are having 2a1, 4a2, 4a2 x square. Just a minute. X raised to power what? Now, can this expression be ever 0? Because 2a1 is positive. We are mentioned here. It is mentioned is a polynomial in which all the coefficients a0, a1, a2 are positive. So 2a1 is positive. So this expression is always positive because the coefficients a1, a2, an are positive, and besides that we are having only even powers of x. So this can never be negative. So the only way this can be 0 is when x is equal to 0. So this is the stationary point which we have obtained, x equal to 0. Now tell me whether this will be a point of local maxima or local minima. Because if you take a point slightly on the left, like minus 0.01, if you substitute, so negative into positive will be negative. So the sign of the derivative, when you take a value slightly on the left, will be negative, because the derivative is depending on x only, right? And this factor is positive. And the sign of the derivative when you take it slightly on the right is what? Positive. So the derivative changes sign from negative to positive. Therefore, it is a point of local minima. So what is the correct answer? Only one minimum. And you know, in these type of questions, you can take a specific case and crack them. If there is a function of this type, right, is a polynomial in a real variable x where these constants are positive and only even power, you can just take x square. You can save time because it is a generalized question. It is a generalized question, true for all values of a naught, a1, an which are positive, and every time this will give you the same answer when the power of x is even. So why to do all this? If you want to just see, you can take a case like this. Like 1 plus 2x square. What is wrong with this? I am just taking the two terms. A naught is what? 1. A1 is 2. They are both positive. A0 is less than A2 x square. You just take a smaller, some particular example, and then you find out what is the derivative. 4x when it is 0, when x is 0. What is the second derivative? What is that? Positive. Minima, or change of sign you can do. Change of sign will also give you the same result. So these type of questions you can take a specific particular case and then solve it. You will be saving time. Next please. Again, on this interval 0, 1, the function takes its maximum value at which point? Try it out. The function is x raised to the power 25. This is question number 15. You have to find at what point it takes the maximum value. And then you have to find the value also. The interval is 0, 1 only. So first you find the stationary point by finding the derivative and getting equal to 0. Then you take the endpoints as well, 0 and 1. And then find the value of at all 3 points and compare. And at that particular point, the maximum value you can find. Just by comparison, it's like absolute maxima. Minus half is not there in the options. At the point, at what point the derivative is 0? Let me check. I don't think it is half, but see how to go about it is first derivative I am finding out for stationary point. See, there will be no point where the derivative is not existing, right? So the only point of local maxima minima which is possible here is which point? The stationary point. I am finding the derivative. First derivative is first function, right, into minus 1. So you can write minus 1 like this, plus this is just 75. It looks as if there's a negative sign here. This is plus, right? Second function as it is, derivative of first. This is 25 x raised to the power 24. Now what, we can take something common? You can take 25 x raised to the power 24, and what else? 1 minus x raised to the power 74. You can take this out. So the second term will give us 1 minus x, and the first term will give you minus 3 multiplied by what? X. So you equate all of them equal to 0. What you will get? Either x is 0 or 1 or 1 by 4. Now you find the value of the function because closed interval is there. Maybe the maximum value is at the end point, right? So what is the value at 0? What is the value at 0? 0 only. Substitute 0 here. 0 into anything is 0. What is the value at 1? Again 0. And what is the value at 1 by 4? It is some positive value. It is some positive value. So obviously when the other two values are 0, right? So this is a positive value. So this is a maximum value which is attained by the function in the interval 0, 1. And at what point it is attained? At 1 by 4. So what is the right option? B, 1 by 4. Next question. Now see, in these questions, you have to first apply Newton-Leibniz formula. You know that? See, in 16th question, the function is given in the form of an integral, right? And you have to find the local minimum at what point? The local minimum at x equals what? This function will have a local minimum at what point? Right? What you will do is first find the derivative. And you know, I'll just explain it to you. You write this. See, this is Newton-Leibniz formula, which gives you the derivative of this phi x to psi x ft dt. It is the value of the function f at phi x multiplied by phi dash x. Phi x is the upper limit, right? Minus the value of the function at this. First you will take the upper limit, then the lower limit. The value of this function at that particular point, and then you will multiply by its derivative, right? What is the lower limit here? It is not necessarily a constant. It can be a function of x. See here you have a function of x. X is given, and the lower limit is a constant. And this, when you will multiply by phi dash x, will ensure the whole thing goes because of the derivative of a constant being 0. So first you find the derivative like this, applying this formula. Now what is f dash x? So in this whole function t et minus 1 multiplied by t minus 1, t minus 2 whole cube, t minus 3 whole 5, when you will substitute what? X. You will substitute in place of t, you will substitute x. So what will you get? In this function fx, ft, you will first substitute the upper limit. So what is the upper limit? X. So what will happen? You will get x e raised to power x minus 1, x minus 1, x minus 2 whole cube, and x minus 3 whole 5. Is this clear to you? And then I have to multiply by derivative of x. See, in this case, it doesn't make a difference. Sometimes if it is a different function like x square, then you have to also multiply this with 2x. So here you can just write 1, right? Because the 1 is derivative of the upper function x. Now minus, in this whole function, if you substitute minus 1, you will get some function, but then after substituting minus 1, after substituting minus 1 here, you will multiply by derivative of minus 1, which is 0. So there is no need to write the value when it is a constant, right? The lower limit is a constant, don't write anything. This is the derivative. So in fact, when the functions are given in this format, the derivative is very simple, right? The same function, by substituting in place of t, if it is in this form, the lower limit should be a constant, and the upper limit, if it is x, you can just, in place of t, you can substitute x, and this will give you the derivative. Now the derivative is there. Now can you find out the local minimum? Find out. Basically we have to just find the point of local minima. You have to find the points of local minima. And what will help you to find the points of local minima? You first equate the derivative equal to 0. Equate the derivative equal to 0. So what points you are getting? You are getting x equal to 0. What you will get from here? Ex is 1. So what is x? Ex is 1. X is equal to, again 0. You take log on both sides. Suppose you take log on both sides. X ln e is equal to what? Log 1. From here 1. From here 2, 3. So many critical points. Now, how you will find out the point of local maxima? Now, suppose this is the line. You have point 0, 1, 2, 3. Right? What will be the value at the extreme? When x is greater than 3, what will be the value of the derivative? Let us take 3.1 or some value greater than 3. So positive, 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 positive. What if it is between 2 and 3? You take 2.5 and substitute in this. This will be negative because the power is odd. Now if you take 1.5, because if you put 1.5, these two will be negative. Yeah, positive आ जाएगा. And if you put a value between 0 and 1, I am just finding out the sign. And with the change of sign, we'll find out whether it is a point of local maxima or minima. Because in case of local maxima, the derivative will change sign from negative to positive. So negative to positive is one point is this. See, this is one of the points. The derivative is changing sign from negative to positive. So it is a point of local minima at 3. Now what about between 0 and 1? Sure. If you take half, positive. You find out. And then you have to take, और फिर लास्ट में भी देखना होगा, दोनों नेगेटिव होंगे, right? So where other place these stationary points, the derivative is changing sign from negative to positive. See again at 1 also negative to positive. So how many points of local maxima are there? Yeah, at x equal to 1 as well as 3. So there are two right answers, B and D. Try the next question, 17th. PQR are three real numbers. Which one of them is correct? And for any three real numbers, P, Q, and R, which of the options is right? You take some values and just keep on rejecting the ones which are not correct. See, when you're taking specific values, you have to ensure that it should be a universal case. One or two, and you have to take a particular case so that it is being rejected. See, PQR are any three real numbers. You find maximum of PQ and then maximum of PQR. Is maximum of PQR is greater than maximum of PQ? Not always true. Suppose P and Q I am taking as 3 and 8. So what is maximum of this? Maximum value is how much? 8. Now if you take a third value which is not greater of, which is not the greatest, let us take P, Q and R I am taking as 5. Now what is happening? The greatest value will not go down, but it will remain the same. So it is 8. So obviously it is not less. This would have been correct if it is less than equal to. When you take more and more values, the greater will not decrease. The greater will not decrease, but the two can be equal also. That case they have not written. So maximum of PQ may not be less than maximum of PQR. The more the values you take, the greater value, the greatest value will increase or will remain the same. So, but that equality sign is not there, therefore the first is wrong. Similarly, the C part is also wrong, because if you take maximum of two values, 3 and 8, it is less than minimum of PQR. So minimum of PQR can be what? Yeah, right? So this is also not valid. Now just check the second case. B part you verify, is it correct? See, one option is just taking some 3 and 8 you substitute and you can find out. If you take 3 and 8, Left hand side is what? Minimum. B part is minimum is what? 3. Now right hand side is what? Half of P plus Q, which is 11, minus what is P minus Q? Minus 5. So mod will be 5. So what is the value? Right? So any two values you have to be convinced, because we have to take any real numbers. We can take negative values as well. Or what you can do is, listen, the other option is you can take P greater than equal to Q, right? If you are not fully convinced, you can take P greater than equal to Q, right? What is half of P plus Q minus mod of P minus Q? In this case, if you take the second option, P plus Q, what is mod of P minus Q when P is greater than Q? It will be same number. Since P is greater than equal to Q, so the mod will remain same. So here P will cancel out. You get Q. And what is the minimum? So similarly, you can take the other option when it is the other way around. P is less than Q. When P is less than Q, this will be P plus Q. And this will be, when P is less than Q, this will be negative. So it will become plus of, here Q will cancel out and you get P as the answer. And since P is less than Q, the minimum is also P. So the right option is B. Next, please. 18th, there is some misprint here. This P is not there. This Px coefficient, in place of P, you write modulus. Try this. The function is, see, the right function is fx is equal to twice of mod x plus modulus of x plus 2 minus, that P is not there. In place of P, you actually, there is a double mod here. So P is a mod sign actually. So this is x plus 2 minus twice of mod x whole mod. This is a function. And you have to find out local minima or local maxima is at what points. The function has a local minimum or local maximum at what points. You just see, here you have to draw the graph. You must have some idea of modulus curves, how to sketch them. Then only you can find out the points. Or you redefine the modulus. Redefine means, in the present shape, you cannot find out how the curve will behave, how the straight lines will be there, what are the points where are the stationary points. You cannot find out in this present form. So you have to redefine the modulus function. How to redefine? See, what are the points where each one of these moduli is vanishing? Mod x is 0 when x is 0. This, so you write this point here, right? From here, what you obtain? Minus 2. Right? But the problem is, here you have moduli inside the modulus. So on solving this and then taking a mod may give you some other points also, where the sharp points are formed. Right? So here in this present case, minus 2 and 0 we have already marked, but you have to take different cases to find out. See how? When x is less than minus 2, right? I'll take the first case. X is less than minus 2. Now, what will be the function when x is less than minus 2? This is negative, so it is minus 2x. Mod of x will be minus x. And if it is less than minus 2, this will be like minus 2.1 you can take. Less than minus 2 means minus 2.1. This will be negative. So you will have minus x minus 2. Right? And inside this also, you will have minus x minus 2, and in this plus 2x. And again mod. We have solved the inner moduli, right? Again there is a modular sign. Now let us see. This is minus 3x minus 2 minus, and what about this? X minus 2. Now x is again like minus 2.1. You can keep that value in mind. X is less than minus 2, you keep minus 2.1 in mind. So when you will put minus 2.1 here, this will be negative. This whole expression is negative. So what will happen? Minus of this. So there's a minus sign outside. So finally, what is this? Minus 2x. Minus 2x minus 4. So here you will have the value of the function will be minus 2x minus 4. Now similarly, you solve when the value of x is between minus 2 and 0. Right? The second case is when x lies between minus 2 and, tell me what it will give you when x is between minus 2 and 0. Let us take some value between minus 2 and 0. You can take minus 1. If you put minus 1 here, this will be minus 2x. If you put minus 1 here, you will get x plus 2 only, right? And here if you put the same thing will repeat. This is x plus 2 and minus 2x. Why plus 2x? I am substituting what? Acha, because, plus 2x. Because I am substituting minus 1. So mod of x will be what? Minus of x. So plus 2x. So now again, this is minus x plus 2 minus. Now 3x plus 2 is 0 at what point? 3x plus 2 is 0 at minus 2 by 3. And minus 2 by 3 is a point which comes in this. So in this whole interval from minus 2 to 0, you will not have the same graph. Because there is a point in between where to the left and right, this gives you different values. Because the sign of this vanishes between minus 2 and 0. And that point is minus 2 by 3. You see, if you equate this equal to 0, you get x is equal to minus 2 by 3. And where is minus 2 by 3? Minus 2 by 3 lies in this, somewhere here. You're getting my point? So now from here, you will have two different values. If you take a value between minus 2 and minus 2 by 3, and then further between minus 2 by 3 and 0, this moduli will give you two different values, one with positive sign, other with negative sign. So what will be the two values? See, first I am taking this interval between minus 2 by 3 and minus 2, this interval. You take any one. First you take this or this. What you will get? Minus x plus 2. Now if you put a value between these two, you substitute minus 4 by 3. Minus 4 by 3. You put minus 4 by 3 here. This is negative. So the value will be negative of this. So it will be 3x minus x is 2x plus 4. You will get 2x plus 4 here. Here you will get 2x plus 4. Here you are getting minus 2x minus 4. And when it is between minus 2 by 3, 0, you substitute, let us say, minus 0.1. If you substitute minus 0.1 here, what will be the value? Positive. So this will be, this is positive. So the minus sign will remain. So minus 3x minus 2. So what this is equal to? Minus 4x. This cancels out. So here the value is minus 4x. Now similarly you find when x is greater than 0. Tell me, when x is greater than 0, what will be the function? We'll think of some shortcut, but once you have to draw the graph. You have to understand why how modulus function behaves. Then we'll try and figure out what you can do to solve it faster. Find out fast. 4x is between greater than 0. This will be 2x. This will be x plus 2. And this will be x plus 2. And this will be minus 2x. Right? So this is 3x plus 2. What is inside the modulus? 2 minus x. Now 2 minus x, if you equate it equal to 0, what you get? X is equal to 2. 2 is in that domain. When x is greater than 0, that means there it will further subdivide. So 2 is the point which will divide this again. When it is greater than 2, what will happen? This will be, when x is greater than 2, this will be negative. So negative होने से क्या होगा? Yeah, minus of modulus will be minus, so this will become plus. So this will give you 2x plus 4. And what about the interval 0 to 2? Obviously, when this is 2 minus x, it will be minus 2 plus x. So this will give you what? 4x. Now we have redefined the function. We have got these linear values of the modulus. Now can you just draw because see, the mod value will never go below the x-axis. Now can you draw the rough sketch? Just try to draw the rough sketch using these graphs. See, at minus 2, the value will be 0. At minus 2 by 3, at 0 and 2, you just draw the rough sketch. See, what is the value at minus 2? If you look at this, what's the value at minus 2? Right? This will be 0. This will be what? 4. And this will be 0. And if you substitute minus 2 here, this will be 4. So the net value is 0. Right? So you will draw the graph of this line. Since the slope is negative, it will come like this. Right? Now, what is the value at 0? If you put 0 here, this will go, this will be 2. This will be what? 0 again. At minus 2 by 3 also it will be 0. Just verify. And then here the slope is what? Positive. It will go above. Forget about the exact shape. It will be increasing. What is the slope here? Negative. It will come down. What is the slope at 2? In between this? 4x positive. And then again it is positive, but the slope is less. Here the slope is 4. Here the slope is 2. So it will continue to increase, but at a lesser pace. So it will tilt slightly like this. You're getting my point? Now, can you find out from the graph? Can you make out what are the points of what you call local maxima or local minima? Fast. See, this point, what? Local minima. This point, local minima. This point, no. This is not a point of local maxima. Every point where the derivative does not exist is not necessarily a point of local maxima. See, if you consider this point on the right, this is the value 2. On the right, the values are greater than 2. So how can this be local maxima? And if you consider a point on the left, the value is less. It cannot be local minima. So what happens, that's point 2 is a point where the derivative does not exist. See, derivative is not existing at these points. These are all sharp points, right? The derivative is not existing. But this is a point of local minima because in the neighborhood of this point, on the right as well as left, the values are positive. This is 0. Here this is a point of local maxima because on both sides the values are decreasing. This is not, it seems to be local maximum, but it is not, because on the right the values are increasing, on the left the values are decreasing. So how many options are there? -2 for local minima, -2/3 for local maxima, and 0 for local minima. So you can just mark the options. So local maximum minimum values are these. At what points? 0, -2, -2/3. So 0 is not there. So -2 and -2/3. In fact, -2 is there. -2 is also not there. So the only option which they have marked is -2/3. -2 is there. So A and B. These are the 2 points of local maximum minima. They have not given all the options. Now 19th. Now 19th you try on your own. This is comparatively simpler. You know, 19th May there is no double mod. Just find out. And try to do it faster. The minimum value of the function fx is equal to mod of 3 minus x plus mod of 2 minus x plus mod of 5 minus x. Question number 19th. Fx is equal to mod of 3 minus x plus mod of 2 plus x plus mod of 5 minus x. So if you draw the number line, what points you will consider where these moduli are vanishing individual? Here, from here you will get what? 3, -2 and 5. So first you write -2, then 3 and then 5. Now find out the values. When you take a value less than -2, first case, what you are getting? Anybody has found out? What? 4 minus 3x. Sure. And what about between -2 and 3? You take 0. See, -2 and 3, you take 0. 0 में क्या होगा? इधर 0 आने से कितना होगा? For this interval. 3 minus 0 is positive. 0 say positive. If you put 0 here, this is also positive. So what you were telling me? 10 minus x. Good. What between 3 and 5? Again 10 minus x. you can substitute 4. If you substitute, listen, 4, if you substitute 4 here, this will be negative, and the next one is positive, and the next one is also positive. X आ रहा है, 0 कैसे आ रहा है? 4 plus x. This is 4 plus x. And finally, when it is greater than 5, minus 6 plus, right? So now what will happen? See the slope, see the derivative. The derivative of this function will be negative. If you differentiate this, the derivative will be negative. What about between minus 2 and 3? Because just see the coefficient, the derivative will be coefficient of x, right? Negative. And here it will be positive, positive. So can you find out, just by this you can make out what will be the minimum value. Minimum value will be when this line you draw, right? Again, it will come down and it will reach a minimum at 3. Then the curve will start rising and this will rise even faster. So the shape will be somewhat like this. It will come down, then it will come further down, then it will reach a minimum somewhere. What is the value at 3? We can find the minimum value as well. If you substitute 3 in this, what you will get? 3 तो इधर भी put कर सकते हैं, 7 आएगा, इधर भी 3 put कर सकते हैं, 7 आएगा, right? So when you have the simplified this function, you can just substitute 3. So 3 will be the point of local minima, and the derivative will not exist at 3 because it will be a critical point where the derivative is not existing because of the sharpness of the curve. Mod function जब बनाएंगे तो वो उधर एक sharp point आएगा. So 3 is the point of minima because see, even the derivative is changing sign from negative to positive, and the derivative is changing sign from negative to positive. It is the point of local minima, and the value will be 7. No, point is 3, but the value will be 7. So what is the right answer? B. 20th. See, this is in this next question, x square minus 3x plus 2 is what? A parabola, quadratic equation. You draw the, find out the point of minima where the derivative is 0. And then at that point and at the end points, you find the value of the function and see which is the smallest. See, the question is find the smallest value of m. Smallest value of m. So this modulus should be less than equal to m. Smallest value of m means what? In fact, this will be the greatest value. Just find, see, what you do is, you find the value of this x square minus 3x plus 2 first. Right? At what points? At the endpoints 1 and 5 by 2 and at the turning point. You find these 3 first. In fact, it is the greatest. They have written to find the smallest value of m, but all values should be less than m. So m will be the greatest value of this in this interval 1, 5 by 2. Find out. So m is the upper bound, you know. For this is the moduli of this quadratic expression, and all the values should be less than equal to m. The smallest value of m will be the least upper bound. You are getting my point. See, here can be some values greater than m. Suppose, let us say m is coming out to be some number. M is equal to, let us say a. M is equal to a, right? All values of this expression after taking modulus are less than a. Now, if you, in place of m, if the value of m instead of a, you take a plus 2. If you take a plus 2, then all values will be less than a plus 2 also. So all those are known as upper bounds. And what is the least upper bound? M. So in fact, the smallest value of m is the greatest value of this expression in this interval. You're getting my point? The concept clear? The smallest value वैसे लिखा हुआ है, but it is the least upper bound. So you have to find the greatest. So what you do is forget about the mod first. You find the value of x square minus 3x plus 2 at these points. I'll take this function fx as x square minus 3x plus 2. Right? What is the derivative? This is question number 20th. 2x minus 3. Equate it equal to 0. This will be point of minima. There's no need to verify because see, these type of parabolas in which coefficient of x square is positive, they will open upward. And the second derivative is also positive. Second derivative positive means what? Second derivative positive means it is concave up. It is concave up. So it is like this. So it has to be this shape. So this point I have to find. This point is 3 by 2. What is the value? You substitute 3 by 2 in this. What will this give you? 9 by 4 minus 9 by 2 plus 2. And on solving this, you will get 1 by 4. Minus 1 by 4. You will take modulus because in the actual function you have a moduli sign also. Right? So when you will take modulus, this value will be equal to 1 by 4 mod of this. And what is the value at 0? No, at 1, the endpoints. What is the value at 1? See, I have to verify. Suppose it is from here to here. This value I have already taken. Then I have to take these two values. Right? 1 पर कितना आ रहा है value? 0. Or what about 5 by 2? You are sure? 3 by 4. So now, see what is happening. 3 by 4 is the greatest value. So the right option is, the right answer is 3 by 4. You know, mod may, suppose this is the, listen, this is the mod at 3 by 2. The value is 1 by 4. The shape is like this. Right? So we have to just find this point and the extremes and then compare. Is that clear to all of you? If there's any doubt, you should ask. Next, please. Now this function, tell me the critical points. It should not take much time. What are the critical points? Find the derivative, equate it equal to 0. See, on finding the derivative, the only critical points will be stationary points. There will be no points where the derivative will not exist, right? There will be no point where the derivative does not exist. So it is very simple. You find that this is question number 21st. F dash x you find. First function. Right? Plus second. What about the derivative of the first? Right? Now you take this common. X minus b raised to the power n minus 1 and x minus a raised to the power m minus 1. So what you will get inside? N multiplied by x minus a. And here you will get m multiplied by x minus b. Now when you will equate this equal to 0, you will get all the critical points. So what are the critical points? B, A, and what else from here? Yeah, if you simplify this, you will get nx plus mx is equal to what? mb plus na divided by m plus n. So now if you look at the options which are given to us, A0, B0 are the only critical points is incomplete because there is one more critical point here. So there are exactly 3 critical points. Now 22nd you will try on your own. I have told you that Newton-Leibniz formula, right? You use that and solve it fast. Let's see who will solve it first. What you have to do is you have to find the derivative f dash x. And f dash x, I have told you that method. In the function, substitute the upper function x. In place of t, you will substitute x. Then multiply by its derivative, which is 1. Minus, in place of the variable t, you will substitute 0. So the lower is, because being a constant, there is no need. The only thing you have to do here is, see, I'll give you time to do this. I'll not solve it now. 22nd May, I'm just telling you the derivative will be of this will be, yeah, f of x. You can write like this, f of x multiplied by, no, you should not write fx is equal to this, because fx, the function involves integral also, right? So what you do is, directly you can write, in place of t, you put x first. In place of t, you put x first, right? See, in place of t, you write x and then multiply by derivative of x, which is 1. And the lower limit is 0. So when you substitute 0, anyways, you have to further multiply by its derivative. So it will vanish, right? So find out the points of local maxima minima. Interval is given to you in 0, 5 pi by 2. Sine function into root x. See, root x will not give you any value. Why? Because this will vanish. Root x will be 0 at 0 only, right? But see the interval. X you have to take open interval 0 to 5 pi by 2. So 0 we don't have to. So that problem is also solved. If some of you might be thinking कि इसको कैसे solve करेंगे, तो root x तो is out. The only thing you have to solve is sin x is equal to 0. Just solve this and find out the points between 0 and 5 pi by 2. Sin theta 0, what is theta? N pi. So if you put n equal to 0, it is the end point. It is an open interval. If you put 1, you get pi. If you put 2, you get 2 pi. 2 pi is also there because the interval is 2.5 pi, right? If you put 3, it is not required. So pi and 2 pi are the only values. Now how to find out which is local maximum, local minimum? Either you find the second derivative, but then second derivative, this root x will also come, right? So what you do is, if you take pi, listen, yeah, if you take pi, left hand derivative, right hand derivative, this change of sign. When I take a value slightly less than pi, this will be positive only, right? But sign of some value which is slightly less than pi will be in second quadrant. Positive. Sin theta is positive. Positive in first. See, sin theta you don't remember. Positive, positive, negative, negative. In first two quadrants, sin theta is positive. After school to college. So this is positive. And when you take a value slightly greater than pi, it will come in which quadrant? Third quadrant. And in third quadrant, what happens? Negative. So the derivative is changing sign from positive to negative at x equal to pi. So it is a point of local maxima. And what happens at 2 pi? तो अभी हाँ 2 pi में प्लस करेंगे Yeah, because if you take left-hand derivative, it will be in the fourth quadrant, right? Can you manage now? So एक pi होगा और दूसरा 2 pi. At 2 pi it is local maxima pi पर, which is the option local maximum at pi, and I think it gives you local minimum at 2 pi. You can verify yourself. 23rd. Now this function has one point of maxima in the interval 0 to pi by 2, has one point of maxima in the interval 0 to, again one. No, the first one is one point of minima, second gives you one point of maxima. Third is no point of maxima and no point of minima. And the last one is 2 points of maxima in this interval. See, the interval which we are concerned about is 0 to pi by 2, first quadrant. Now, who will solve this? First find the derivative. I'll give you a hint. First find the derivative and try and see what you get by equating it equal to 0. See, in all questions of maxima minima, the first thing which comes to your mind is finding the first derivative and equating it to 0. Because even if it is absolute, those points are to be checked. Fx is equal to x upon 1 plus x tan x. This is the derivative. You see whether you're getting this. 1 minus x square, sec square x upon 1 plus x tan x whole square. Right? Now, what we have to do? We have to find the point of maxima minima, whichever is possible here. So for the at what point you will have local maxima minima or absolute where this is 0, right? Because we are not given, interval is given between 0 and pi by 2, right? Now, if you solve this expression, this will be 0 when 1 minus x square into sec square x is 0, right? Now, this gives you 1 is equal to x square upon cos square x. This expression will be 0, derivative will be 0 when cos square is equal to x square. You agree? The derivative will vanish when cos square is equal to x square. Or you can say cos x is equal to plus minus x. This derivative will be 0 when cos x is either equal to x or value of cos x is equal to minus x. Now see, if you draw the cos curve is like this. And we are only interested between 0 and pi by 2. Cos curve is like this, the shape of the cos curve. Cos 0 is 1 and cos pi by 2 is 0. Why I have drawn this part of the curve? Because everywhere the domain is 0, pi by 2. Now, what will be the line y equal to x? Y equal to x will be a line passing through origin and going like this, right? And now see, if you look at slightly more, if you increase the interval, the cos curve will also be like this, and y equal to minus x will go from here to here. But we are not concerned about that because the interval which is given to us is 0, pi by 2. So at what point cos x is equal to x? This is a graph of y equal to x, right? This is a graph of y equal to x. Oh, this is a graph of y equal to x, and this is y equal to cos x. This is a point where cos x will be equal to x. So there is a point. There is a point where these two are becoming equal, and this expression will become 0. So at least we have confirmed one thing, that there is a point at which this differential is 0. And there are 2 points, one on this side, other on this side. The other point I am not taking because of the interval. So at this point, You have to just verify whether it is a point of local maxima or it is a point of local minima. How you will verify? This point, let us say, is alpha alpha, some point, right? See whether you can find out. Second derivative will come out to be negative. Therefore, in this case, there is one point of maxima in the interval 0 pi by 2. There is one point of maxima. Achha, next. See, these are slightly tough questions. They are abstract in nature. You have to understand them, and then it will take some time to settle down. See the 24th question. All of you read the question, take your time, and try to make out what the question is. In this question, the function fx is defined as sine inverse lambda plus x square when x lies between 0 and 1, and it is equal to 2x when x is greater than equal to 1. It is piecewise defined, right? There are two different intervals which are given, and you have got two different functions. Fx can have a minimum at x equal to 1 if value of lambda is. So what they are trying to ask you is, if for this function fx, a minima exists at x equal to 1. If the minima exists at x equal to 1, then what should be the value of lambda? So basically it is find value of lambda so that this function gives you a minimum value at x equal to 1. Now think about it, take some time, and at least tell me what we should do. Find out. So for the point of minima, when x is the point of minima, x equal to 1 is the point of minima. That means at x equal to 1, the derivative should exist, or it should, if it exists, it should be 0. Or the derivative should not be, it can be a critical point, derivative is not existing. So what we do is we find the derivative and see that the derivative should exist at least the derivative should be equal to 0. Just find out from these two cases. Let me find out the left-hand derivative. You know what are the limits for left-hand and right-hand derivative? A function is differentiable at x equal to a if the right-hand derivative at a and the left-hand derivative at a are both equal. Why I am finding the left-hand and right-hand derivative in this case? Because it is piecewise defined. That means at x equal to 1, when you go to the right of 1 and when you go to the left of 1, you have different functions. So what I do is, I find a left-hand derivative at 1. So I'll write 1 minus h minus f1 upon the difference of these two. And I'll take the limit. This is the value of left-hand derivative. And what will be this equal to? See, when here, what is the value of this expression? Slightly less than 1. When it is slightly less than 1, what function I'll take? Sine inverse plus x square, that is 1 minus h square, right? And what is the value at 1? Value at 1, this function will be used. The second function, 1 is closed, so minus 2 upon. Now, since we want this what you call limit to be defined, what should be the value of sine inverse lambda? Let me simplify this first. Sine inverse lambda, on opening this you will get 1 plus h square minus 2h minus 2. So this will be minus 1 upon And limit is also very important. You should keep on writing limit. And what is the right hand derivative? Right hand derivative when x is slightly on the right side of 2. Sorry, right hand derivative when x is slightly greater than 1, it will come out to be 2. So this should be equal to 2. Then only we can say that the function is differentiable. The left hand derivative and the right hand derivative should be equal. Right hand derivative, you have to use this function 2x. So the value will be 2. So when will this be equal to 2? See, if you just see sine inverse lambda minus 1 is a constant. And if you simplify this and this cancels out, you will get 2. And this is minus h. Limit s tends to 0 is equal to 2. Right? Now this is equal to 2 when this is 0. See, this expression will give you the value 2 if these two cancels out. Then only 2 will be left. See, when you take the limit h tends to 0, this will go. So only 2 will be left here. So this is an additional quantity which we don't want. This limit should be equal to 2. Now the limit of this is 2. If you consider this function, if you consider the function I have put in a box, if h is tending to 0, what is left here? What is the value of this? 2. So you will get 2 from here. This sine inverse lambda minus 1 is a constant, which we don't want it to be for this limit to be equal to 2. So these should cancel out, or the value of this expression should be 0. So sine inverse lambda should be equal to 1. So sine inverse lambda should be equal to 1 so that the function is differentiable. But that is not enough. We want the function should have a minimum value at 1. It should have a minimum value of 1. So that means the derivative should change sign as well. The derivative should change sign as well. Now let us see x equal to 1. If you find the left hand derivative, what is the sign? And then the right hand derivative. So we have found out there is some lambda. See why we are doing all this. Up till now what we have found out? That there is some lambda for which the function is differentiable at x equal to 1. Derivative exists, there is some lambda. But now we have to find out that whether the change of sign is taking place or not. If you find out the left hand derivative at 1, sine inverse lambda is 1 now. Sine inverse lambda is 1 now. So left hand derivative at 1 will be what? What is now, if this is 1, what is the left hand derivative? 2x. And what is the right hand derivative? 2. See the derivative. Now x equal to 1, we have to just find out whether the change of sign is taking place or not. Because हमें minimum निकालना है ना. This should have a minima at x equal to 1. So minima at x equal to 1, अभी हमें check करना है what should be the value of lambda. Now lambda is coming out to sine inverse lambda is coming out to be 1. So what is the left hand derivative? बताइए. Left hand derivative will be 2x. Now when you put 0.9 in this is coming out to be positive. And what is the right hand derivative? So what is happening? The sign is not changing. So in spite of there existing a lambda for which the derivative is there, the change of sign is not according to what we want for it to be a point of minima. Therefore, none of these. You're getting my point? Had it been positive to negative, then it is a point of maxima. Or agar ye negative to positive hota, then it would have been a point of minima. Then value of lambda we would have calculated from here. Lambda would have been sine 1, right? So in fact, to save time, why I did all this? Just to make you understand the concept of derivative. How to find out the derivative in case of piecewise defined function. That was what I wanted, just to learn these limits. But otherwise, what you would have done, we could have substituted some constant value. sine inverse lambda, we would have substituted some constant value, and then we would have found out the change of sign first. You're getting my point? Then this whole time we would have saved. Suppose there exists a lambda, you assume that, right? Lambda is some value a. You substitute sine inverse a, right? Then you find the derivative. Derivative, left hand derivative is 2x, right hand derivative is 2. And then at x equal to 1, you can find out the change of sign is not taking place. So that means minima is not possible. So if you would have reversed the order, then you could have solved it faster. The next please. Question 24. Last two steps, what we have done is, basically this question says you have to find fx as a minima at x equal to 1. Fx as a minimum value at x equal to 1, there is a minimum value. Then what is value of lambda? So the order in which I have done was, I explained you how to find that, how to check the derivative at x equal to 1. So to check the derivative at x equal to 1, we have to find the left hand derivative as well as the right hand derivative at x equal to 1. So right hand derivative and left hand derivative are the limits. We use those limits of the derivatives. And then we have found out that the value of the lambda is equal to, sine inverse lambda is equal to 1 for the two limits to be equal. So that means the derivative will exist if sine inverse lambda is 1. The derivative will exist if sine inverse lambda is 1. But at x equal to 1, we found the change of sign is not taking place. The change of sign, you can even do it without finding out the value of lambda. The change of sign is not taking place. But had it been the change of sign according to the point of minima, then we would have able to, still then we have to find the value of lambda, because the actual question is to find the value of lambda. After removing h from denominator of limit. See, I'll just write one or two steps here. See, if you split this, sine inverse lambda minus 1 upon minus h plus h you take common, h minus 2 upon minus h, right? Limit h tends to 0 and limit h tends to 0. Right, this cancels out. So this gives you, this minus will go up and you will get 2 from here, right? So the value of this limit should be equal to 2 because the right hand limit is equal to 2. Here the problem is we are already getting 2 here. So this value should be equal to, this should not exist. So if sine inverse lambda minus 1 is 0, if sine inverse lambda minus 1 is 0, then this expression will go. Otherwise, this will create problem. Here, if you have to find the limit, what you will do? See, if sine inverse lambda is taking some value not equal to 1, I am saying sine inverse lambda should be equal to 1. Suppose it takes value some value other than 1. Then what, you know what this limit will be? This limit will be infinite. It will not converge. It is a divergent limit. This is a divergent limit, means this will tend to infinity or maybe minus infinity, because the value which you will take. So it will either be, it will not be defined. So then the differential will not be defined. So the only way the left hand derivative and right hand derivative can be equal is if these two cancel out each other, and these two will cancel out each other only when sine inverse lambda is equal to 1. So that at least we can find the limit of the remaining part, which is equal to 2. Hence the derivative is existing. But here there is no value because the change of sign is not taking place. I think that resolves your query. Next, please. 25th question, you know, we have discussed in the previous class also, in which, yeah, the curves were, one was rectangular hyperbola, other was a straight line, and then we found out that both local maxima and minima are there, and the local minimum value was coming out to be greater than local maximum value. So in this, the right options were, what were the right options? Maximum fx was less than minimum fx, and it had both a maximum. So C and D were the right options. Now 26 you try. Find the critical points of this function. Let's see who can do this. You have to find the critical points. And it seems to be a very simple question. I can even give you the value of the derivative. (26th question), the derivative is coming out to be this. Minus x square minus 14x plus 1 upon x square minus x minus 6 is equal to 0. Now you have to tell all the critical points. This is a derivative. No answer yet? Now it should not take much time because critical points we have taken so long to explain. Two n minus 3 is not there. इधर तो 3n minus 2 है. What it is coming out? No, if you, this is the derivative. Your derivative is telling with this, right? See, what I am asking is your derivative is this. So what? How to find critical points? Either the derivative should vanish, derivative 0 hoga, or derivative should not exist. Now here in this question there is a catch. Right? I gave you a hint in the beginning also. If you equate this equal to 0, probably you are getting these points. Minus 7 plus 5 root 2 and minus 7 minus 5 root 2. This is by solving the numerator equal to 0. So when you will solve the numerator, if you find the derivative, solve the numerator equal to 0, you get the points where the first derivative vanishes, right? So these are the two critical points. But now you take the denominator equal to 0 for points where the derivative does not exist. And what values you get? 3 and 2. X is equal to 3 and minus 2. So what are the critical points? Anyone who differs from this view? Somebody first said only C and D are the critical points. Who said that? That is the right answer. That is the reason I am asking you. So one of you said that only C and D are the critical points.
So if x square minus 6 minus 6 will be 0, then the function will not be.
Yes. See, in this case, the denominator of the derivative is vanishing at the point 3 and minus 2. And if you look at the denominator of the function, that also vanishes at 3 and minus 2. It is the same function, x square minus x minus 6. The only thing is here we have squared it and there it was not squared. So why these two are not be the critical points? Because in the definition, which I started with the definition today, and I told you that what you have to keep in mind is if a function is defined in the domain D, then the points are critical points. If either, that first thing is that the point, listen, x equal to a is a critical point if it x equal to a should belong to the domain, and then up it should be in the domain, and then the first derivative should be equal to 0 or the first derivative should not be defined. Here the first derivative is not defined, but that point makes the function not defined. Therefore, these points 3 and -2 are not in the domain of the function. So hence in critical points you will not consider these. So what are the only points, critical points? C and D. Now let us see who can do the next one, 27th. Again you have to find the critical points. This one should not be a problem, because here 27th f dash x is what? 6 and -12. No, it will be +12. Sine 3x. Right. So what is sine 3x equal to? -half. Right. So how to solve? You know these trigonometric values, general solution. What is the value of theta which will be -half? You half is at pi by 6. So what you do? Pi plus pi by 6. So it is 7 pi by 6. See, general solutions are always better because they give you all the values. At times you just write particular solution, you may miss some of the values. And especially when this domain is larger. Instead of 0 to pi, if it is 0 to 2 pi, you may miss certain values. So what you do is, sine theta is sine alpha. Theta is equal to n pi plus -1 raised to the power n into alpha, right? So what is x equal to? This 3 you can write here. Right? And now just substitute and find out when the derivative is equal to 0. See, at all points the derivative is defined. There is no point where the derivative is not defined. So you need not worry about that. So I think 7 pi by 18 and 11 pi by 18 will be the right answer. If you put n equal to 0, you get 7 pi by 18. And if you put n equal to 1, you will get 11 pi by 18. So what are the two critical points? 7 pi by 18 and 11 pi by 18. Next, please. The critical points of this function. Final answer of 26. What was 26? See, the final answer is C and D, because what we did was at 3 and -2, the denominator of the derivative is becoming 0. But why A and B were not, 3 and -2 were not taken as the critical points? Because at those points, in spite of the derivative not defined, the function was also not defined. So the final answer of question 26 is C and D parts, the option C and D. Now 28th. So the derivative is coming out to be this is the derivative. Now what will be the critical points? Exponential can never be equal to 0. You must know that exponential is always positive. Asymptotic बनता है to x-axis. So this one will be 0 when x is equal to ±1 by √2. So what is the right option? C and D. Now see if there is any catch in this 29th question. This is the derivative. X multiplied by 2 log 3x plus 1. And what you have to do is, you have to see when this is 0. Either x is 0 or this log function is 0. When is log function 0? You know log 1 is 0. Log 1 is 0. So 3x plus 1. So x is equal to. So you have this option. It's coming out to be different. This is not 3x. Just see whether the derivative is correct or not. Find out the derivative again. Find out the derivative again. See, first function, what is derivative of the second? 3 by 3x, so it is 1 by x, plus second function. What is derivative of first? 2x. There's, I think, some problem with the derivative. You find the derivative again, this cancels out. So if you take x common, you get 1 plus what? 2 log 3x. Now you equate it equal to 0, right? Either x is equal to 0, but what? Minus half. Log 3x is equal to minus half. And then what you can do is 3x is equal to what? E raised to the power minus half. You know this exponential form. This is the base is e. Natural log is there, so base is e. So x is equal to, e raised to power minus half by 3, which is nothing but 1 upon 3 root e. So we just, the right option is what? The first option is the right option. Similarly, you can find the next question. 30th question you can do on your own, right? Now, 34th you see whether you can. 34th, was hardly any time left. So there are few questions which I want to discuss. See, in 34th question, it is not a maxima minima. Fx is a function which is log of log sin x plus a. Inside you have base 3 and outside 1 by 3. Now you know the base will make the difference in the log function. If the base is see, it is decreasing for all real values of x in which interval? Now listen, when the base, what is base of a log? It can never be 1. Base of log function is never 1, and it is a positive quantity. Log of base is a positive quantity, not equal to 1. But when the base is positive, the behavior, the curvature is like this. Positive base greater than 1. If the log e is greater than 1, so when the base is greater than 1, it is monotonically increasing function. When base is less than 1, like in this case the base is 1 by 3, right? When the base is 1 by 3, it will be this type of function. So if sin x is decreasing, fx will be increasing. and vice versa. If sin x is increasing, the function fx will be decreasing. So here, such a case is not possible. See, you have to just think about these graphs. When the value of what you are finding out, log of sin x plus a. So if sin x in some interval, the sine curve will increase. So when sin x will increase, this value will keep on increasing. So these bases you have to take into account to find, yeah. So when sin x will increase, so therefore such a case is not possible. It will keep on alternating. Next, can we just go through this question 35th? Fast. See the number of critical points for this function. Maximum of sin x cos x, right? Sin x graph is like this, between minus 2 pi and 2 pi. Oh, this, I'll draw it again because I have to draw it from minus 2 pi to. And what is the cos curve? Cos curve will be like this, right? Now you have to take the maximum of these two. So maximum of these two is the one I am marking it like this, the one which is above the 2. That is the maximum curve. So what are the points, critical points? This is a critical point 1. This is a critical point 2, 3, 4, and maybe there are 5 critical points, because at all these points the derivative is not existing. The derivative is not existing, but they are point of local maxima or minima. So I think we have left out 1 or 2 points. The right answer is there are 7 critical points in this. You draw the curve of both sin x and cos x between 0 and 2 pi, and you just take the upper part. Which one is above? You take that. So this is a critical point. The derivative is not existing. This is a critical point. This is a critical point. This is a critical point. You draw it neatly and properly, you will find there are, I think, 7 critical points. That's all for today. Thank you.